Wow, Neil Armstrong. Hey, wait a minute. You're supposed to be on the moon. I just saw it on TV.
Oh, there's a tape delay and with all solar winds.
Productions.
Nobody that I know of in my field uses the so-called scientific method. In our field, it's by the seat of your pants. It's leaps of logic. It's guesswork.
You don't see the curvature of the earth. That stuff is flat.
GLOBEBUSTERS taking over. Bye-bye, moon man and rover. NASA's so mediocre. Sorry, but your ball is dead. But your ball is GLOBEBUSTERs taking over. Gotta ride this roller coaster. But the truth is getting closer. Sorry, but your ball is dead. But your ball is. Get the shovel for the slice of a piecing up the puzzle. Need a burst of bubble. Evil gonna crumble, yeah? Sit down, be humble. Got the ball, you better fumble. You'll get mad, cause at this fight I'm about your uncle.
And then they call me the liar. I mean, it's absolutely unbelievable the pathetic techniques that they have to use to prove their heliocentric model.
Vibes at the president, Jan got your evidence. Arrows laying desert wisdoms, that shark is evident. That the earth electric and it's resonant. Your residence is heavens, and I hope you settle in like some sediment. If we so wrong, why they lying to discredit it? That's not too intelligent. That's a guy, not a in court, but we ain't really in the settlement. It's time to awaken from the pseudoscience sedatives.
GLOBEBUSTERs taking over. Bye-bye, moon man and rover. NASA's so mediocre. Sorry, but your ball is dead. But your ball is GLOBEBUSTERs taking over. Gotta ride this roller coaster. But the truth is getting closer. Sorry, but your ball is dead. But your ball is.
Inner World Productions.
We accept the reality of the world with which we're presented. It's as simple as that.
Hello, everybody, and welcome to another edition of GLOBEBUSTERS Tech. I'm your host, Zach. Good times for all. And tonight we'll be covering on the orders of measurement and experimentation. It's going to be a really special show tonight. We have a guest who's going to be presenting. A very, very wise young man who I've learned a lot from already. Just listening to him give these types of presentations, it's really in depth. This is what tech is all about. This would make Bob very proud to see this happening tonight. So without any further ado, I'm just going to say hello to the panel, and we're going to get right into it. Starting off, I'm going to say hello to Mr. Kyle Adams. Kyle, how are you doing today, sir?
Doing really, really well. Just one adventure after another. Yeah.
Awesome sauce, man. And next up, we have Mrs. Cammie Nodell. Cammie, how are you doing, ma'am?
I am doing good. I am wishing Karen B the happiest birthday ever. Karen is out to dinner with Ted right now, and we want you to enjoy your dinner. She may be joining us a little bit later in the evening, but warmest birthday wishes. And even though it's her birthday, somehow I got a present. I'm going to mention it just because everybody, I think, should go online and get this. It's not an album anymore. I guess it's a CD, but I got a gift from Conspiracy Music Guru, his Esophageal 2 CD, which is now out. And I have to say, I'm mesmerized. It is so, so good. And so setting a nice relaxing mood here. But I did want to shout that out and say thank you to you, Alex. It's wonderful. I'd like to, again, be able to share it with everybody out there. I highly suggest you get it. It's, again, fabulous.
Absolutely. I have only got to hear a very little bit of it because Cammie wants to listen to it with her headphones on. So I don't even get to listen to it all that much yet.
Alex said that is the experience, so I'm doing it. It really, really is nice. So I'm enjoying it a lot. And with that, yeah, I'm very, very excited for tonight.
Well, all right. Well, let's say hello to our guest. You may already know him. He has been very busy and active of late. He's all over the place. On YouTube, he has a channel, and on Rockfin, I believe, called Space Audits. Alan, welcome to the show, sir. How are you doing this evening?
Doing fantastic. Thank you for having me on. It's an honor to be here.
Well, thank you so much for coming, man. I've just been so impressed by the work you and Toby and Sean are doing over there. It's really just really something that the flat earth needed, that kick in the butt, that tech, they're really digging into the meat and potatoes of what's really going on. And I think you guys are doing awesome work over there. So thank you for all the stuff you guys are doing.
Yeah, it's been awesome, man. We've developed like a full-time staff community out of it. It's awesome. We even have Globe people that contribute to everything, and so it's awesome, man.
Yeah, just amazing stuff. And how well structured it is what really keeps me around and coming back and listening. It's not, just people screaming over each other. You actually make people finish conversations. It's not, oh, well, you got me, I'm going to just obfuscate and then move on to the next topic. It's like, no. Yeah, I love the way you guys handle it. It's perfect. We needed it. Yeah. So what do you got for us tonight, man? You want to give a little rundown about what it's going to be about, or would you like to just jump right into it?
Yeah, so the intro is kind of just jumping into it. That explains the intro is included. That part is included. So we can jump right into it. So I'll just change scenes here, and we should be good to go with that.
All right.
All right, cool. So the purpose of this presentation is to lay out a philosophical framework, state those principles, go over the scientific method, come up with an objective way to look at reality and interpret experimental results to determine, where you live, right? So, and in doing that, we're going to go over the history of light, because that is one of the most significant things in physics. And it's, its importance is, can't be understated, really. The interpretation of light and how it behaves is like the fundamental root of everything, really, especially the belief systems about how the earth is in motion and all that sort of stuff. So we're going to get into that and see if we can't figure out a logical, coherent way to interpret the world. And then we're going to go over the experiments that the mainstream say, prove X, Y, Z about their interpretation of the world. We'll do a little compare and contrast.
Yeah, awesome, I just want to say something real quick on that. With light, it's a really big deal because when it comes to think about all these different laser tests that flat earthers are continually out there doing, all these observations, long distance observations, it's all very much pertaining to light in the way that works. And so when it comes to really understanding that, that's fundamental when it comes to everything flat earth, pretty much.
Yeah, it's, it's in control of one of our most important senses that we use to observe the world around us.
Yep, absolutely, man. Like I said, can't be understated. And then the fight over the correct interpretation is, been a battle, centuries old, right? So let's get into the history of all that. But before we do that, we'll establish what is the scientific method, because, some people have their own interpretation of it. So we'll lay out ours. We start with an observation. We define a problem based off of the observation. We make hypotheses on how, we could solve that problem, or what it might, what might be the causal mechanism, et cetera, right? Then we conduct experiments to test that hypothesis, and then we derive theories based off of that experimental evidence, right? Was our hypothesis falsified, or did we get some evidence to support it, right?
And sometimes you don't know. Sometimes there's not even a problem that you even observe. You're just making an observation of something, and yeah, there is no problem, right?
Yep. All right, and then we have, for our philosophical framework, will be philosophical realism. So with that, it'll be accurately portraying reality, making the least possible assumptions and assertions about things. You're avoiding idealizing or romanticizing mathematical abstractions and vague explanations for things. And you'll get your proof through logical deduction, and you should be able to present your line of reasoning to someone without it, without contradiction. So that is the philosophical framework of interpretation that we'll be implying for all this. And then there's two more key concepts to understand as we go through these experiments, and that's going to be first order and second order, and that could be broken up to the type of experiment. Is it a first order or second order? Or it could be the type of measurement in the first order, second order, or it could be, so that would be like a direct measurement or indirect. And then you could do second order mathematical derivations and analysis. So that's, and the importance of that will be, we'll go over that as we continue on. So in a first order experiment, we're going to look at a topographical view of an interferometer setup. On the left here, we have the Michelson-Morley setup. So this is called an orthogonal setup where a light beam is split at a right angle to itself. Now, the way they had their apparatus configured with these mirrors, the light beams are bouncing back and forth. So they say that that's a second order experiment because the light's going like there and back. And then we have a closed loop circuit on the right. So in this configuration, the light is all traveling in the same direction. And they would say that that would be a first order experiment because it's, it's going in the one way, right? All right. So hopefully that breaks that down. And then to kind of reiterate that, so in chemistry, a first order reaction is one in which a rate of reaction is proportional to the concentration of the reactant. So when you can get a direct 1-to-1 ratio with what you're measuring of the cause and effect of it, when it's a 1-to-1 ratio, that's a first order effect. So in the case of interferometry, the directionality of the interferometer would case of the interferometer. Actually, sorry, I skipped that part. All right, so first order and second order math. So you could do V over C, that would be a first order math analysis of it, or you could do a higher order approximation where you would do V over C squared or V squared over C squared, stuff like that. You're just getting a higher order. V would be velocity.
Velocity, okay. Because
So to touch back on the first order relationship, so a large portion of what we're going to be covering here is interferometry and how it measures velocity and how they derive that relationship.
So we're talking about the speed of light exactly, or?
Yes. Yep.
Okay. So we're talking about the speed of light, and V is velocity and C is
speed of light.
Speed of light.
Mm-hmm.
Okay.
Yep.
Okay. I've been talking a lot about electronics lately, so I'm thinking volts right now. I'm sorry.
Oh yeah, you're good. You're good. All right, so let's see. Higher order approximations, and that about covers that. Okay, so now we're going to get into a little physics history with Newton's bucket. And sorry if this slide, no, it didn't really. Hold on one second. See if I can get it to get a little bigger. Nope, that's not going to work.
Is it just a half image there?
Yeah, sorry about that. It's cut off at the top. It's supposed to not look like that. But anyway, so what we have is Newton's bucket. This is a scenario where we have Newton spinning a bucket and he's trying to make a prediction with his equations, right, for a centripetal force. So if you apply a centripetal force to the bucket, you see that the water spinning, you apply that and it predicts that there will be a depression in the water as it's spinning. Now, this is correctly interpreted from the lab frame, which is where Newton is standing, right? So he's standing on the earth, which is the lab frame, spinning the bucket. He knows he's stationary. The bucket's in motion. Apply the equation to the bucket. You get the prediction for the depression of the water. Now, suppose you have a little lad inside of the bucket, and he's the bucket lad. Now, when the bucket lad is getting spun by Newton, he's stationary in his frame. He's seeing that the water is depressed and that Newton is spinning counterclockwise, right? Because Newton's spinning it clockwise. So anyway, the bucket lad sees Newton going clockwise, and he predicts that his velocity in his frame is 0. So he predicts that the water will not have a depression, and it's not. That's obviously not the case. So it makes the incorrect prediction. So when Newton proposed his 3 laws of motion, this was the being in a frame of acceleration being in rotation was the exception to that. So he said that there was an absolute space, but he didn't know where to put it. So they just said that it's with respect to, the stars or whatever, right? Just some abstractness because Newton was a Copernican lad. So the Earth obviously couldn't be the absolute rest frame. So he said that it was probably with respect to the stars. And then the second slide that's cut off a little bit is Ernest Mach, who the mainstream interprets as saying that the laws of relative motion, the physical laws relate to the motion of the distant stars to the local inertial frames, and local laws are determined by the large scale structure of the universe. His actual quote was, "Such forces are produced by the relative rotation with respect to the Earth and other celestial objects." So he was half right. It's with respect to the Earth, not the other celestial objects. So the important interpretation here, the important takeaway, is that the laws of physics were derived in the lab frame. They apply in the lab frame, stationary, non-rotating frame. And when you're not in that frame, that's where the laws of physics don't apply. They make incorrect predictions, right? So that's the baseline that we're going to be starting with, is that the Earth is the lab frame, stationary. The absolute rest frame isn't with respect to the absolute stars. With respect to the stars, it's with respect to the Earth. I'm sorry. The lab frame is the Earth. My bad. Okay. So with that understanding of the philosophical framework to jump off with, we're going to get into kinematics and dynamics. Kinematics is a measurement. It has no concern for causal mechanisms of force to cause motion. You're just measuring, hey, there's a thing here. It moved to point B. How long did it take to get there? Then we could do derivatives and figure out, how much acceleration there was, when it'll get here, how fast it was traveling when it got there, et cetera, right? And then dynamics would be analyzing the full system and applying forces to predict that motion, to say that, that motion itself was caused by XYZ force. And then you would make, then that's where you would start to get physical laws based off of the accuracy of, your dynamics when you're accounting for actual real forces of the causal mechanisms of motion. So that's kind of how physics is.
From what I'm gathering, what you're talking about there with kinematics, it's talking about observable things. When I push this happens, and that's something I can physically observe right now. But dynamics is thinking much more into the future. I get a chain reaction. If I do this, it's going to set off a chain reaction to things that haven't happened yet, but it can happen. Is that right?
No, close though. So kinematics would be just measurements in regards to motion. It doesn't matter if it's real or not. Like, it could be a hypothetical scenario. You're just tracking objects that are moving, right? So think about, like, you're watching NASCAR, you're watching the car go around the track. You would be like, okay, the car is here at this time, and then now it's at this point 2 seconds later, and then you would be able to plot how fast the car was going, et cetera, right? Based off of that. Like, you're not concerned with, how much fuel does the car have? What's the aerodynamic drag? What's the tire friction on the road, et cetera? That would be dynamics. So for kinematics, you're just concerned about future predictions of motion based off of the velocity that you're observing. And then dynamics would be why that velocity is happening.
Okay. This is what we observe, and this is why we observe it.
Perfect. Yep, exactly. Okay. So they have physics broken into two separate parts of that. So one's just like analyzing and making predictions, and then you test those predictions with dynamics. And it should be noted that all dynamics starts with a stationary lab frame. There's no dynamics that are done in from an accelerated point. Like, it all starts stationary, non-rotating for their predictions. So that's like, when it counts, when it matters, everything starts with that. But where's that absolute rest frame again? It's the Earth. It's the lab frame.
It's always
right?
the Earth. Yeah.
Oh, we found it. It turns out it's not the stars. It was the Earth the whole time. All right.
Yeah. I've been looking into that. The whole absolute reference frame. That's a really big property in Newtonian mechanics. And
it's huge. It's huge, especially when Einstein came around.
So I think it was Boston University that was talking about that, about the whole absolute reference frames, how that's like an essential element of Newtonian mechanics.
Yep. So we have proof by logical deduction. So some examples here would be, if the antecedent for gas pressure is containment, it would logically follow that there must be a container. Similarly, if there's a wave, there must be a medium for the wave to be woven in. I don't know if that's the correct phraseology, but I feel like woven is the way to go with that. So anyway.
I like it.
So Newton's laws of motion, like I was saying, were derived in the lab frame. They apply in the lab frame. We all know where they apply. Oh, dude, that's why it's all messed up. Oh, there's an man, Bennett's hiker. Hold on. Let me see if I can 'cause that's a lot easier to understand
Yeah, no rush. Go ahead. Take
than
a
the
minute.
bucket. Let me see if I could pull that up correctly. Because that would be a huge shame to miss out on the bucket. Bennett's hiker.
Daryl Davis says, shout out to the Misfits. Shout out, Daryl Davis. Super Flurf in the chat. Riley O in the house. We got Mark, just Mark. Run Boston Bear. Much love, brother. David Reif here. Angle of Elevation. Chilster Deluxe. Toby Walker in the house. CJ.
Let me
Awesome
see
from
if
the
I
Mellow
can-
Dome. There we go.
Close enough. All right, cool.
All right.
All right. So real quick, back on the bucket frame and who makes the correct prediction, et cetera, right? So an easy way to look at that, because they might say, okay, well, that applies to angular rotation, man. Obviously, there's an absolute space for that because there's a fixed point of origin for, for the rotation to happen. You could trace it back to the center of it, right? Now, for linear motion, it doesn't apply. Well, when you have a car and someone who's stationary on the side of the road, you apply the same things. This is Bennett's hiker. You apply Newton's equations for acceleration of the car frame. Driver feels the inertial force, and then you apply that to somebody on the road and they feel no force. So hopefully that makes it a little easier to determine the correctness of the frames, right? And like where the laws of physics apply, because they say that we're, rocketing through space and all this stuff. There's all this motion going on, yet we don't feel any of it. And the laws of physics apply to this frame for some reason.
This gets me thinking about Dr. Perez gives his video on PBS Space Time where he does the whole Newton versus Einstein thing, and saying that Newton shows the Earth at rest. Einstein says that the Earth is not at rest; it's actually accelerating up to the ball or the apple that you drop. And I thought that was really wild. And that's where he kind of starts to talk about these standards of non-acceleration, and that was a really key point right there, I think, in the whole presentation. Though yeah, it was kind of really fast and kind of wonky in some places, but yeah, it's an interesting one.
Yeah, absolutely, man. All right, so okay, we know that we're stationary. We got our philosophical framework of evidence, so we're going to look at evidence and then we're going to see how does it apply to reality. What assumptions are we making to interpret it, right? And are we making the least amount of them? Is what we're doing, is how we're interpreting reality logically coherent. Okay. So, did that. All right. So now that we've got our framework, we're going to go over the history of light now and get into that. So for a long time, it was discovered a long time ago in the 1700s. There was a guy named something Bacon, and he noticed that there was that light from the sun was being diffracted in his glass, and it made a rainbow projection, right? So from that, we have that was Roger Bacon in 1219. Sorry, not 1700s. So that was Roger Bacon, 1219. So he notices that light is split into a rainbow, and then from there we have Newton, who comes along and he does some further experimentation on it. That was the early documentation. There's not much on the Roger Bacon guy. Pretty much it all comes from Newton. So we got Newton with his prism here, and he's his experimentation was to figure out if the color was encoded in the light beam or if the material objects added the color. So when you put the light to the beam, it splits, and he's showing that the color, when it diffracts back, is doesn't come from the object. It comes from the light beam itself. It doesn't matter what color the beam itself is. It's all encoded in there. So that was a important experiment to get things jumping off, and that would be a first order effect in light. So what he's doing here is he's introducing a medium, and it's causing the light to split out into the rainbow pattern. And so that's all we really have for that.
He's dissecting the light and then he's putting it back together again.
Exactly, splitting it open, seeing what's in there, putting it back together, because that was a part of the debate back then. Was like I said, is it in the material object or is it in the light itself? So Newton settled that one. And then we have Joseph von Fraunhofer in 1700s to the early 1800s, and his contribution was, instead of using a prism, they found that using a diffraction grating, you could make even finer measurements, right? So even back then in the early 1800s, they had like diffraction gratings that had 75,000 slits in them. So you could get really precise with this. And then you would have a wire of a known thickness, and then you would take your measurements with that against photographic plates. And that's how they would break down all these wavelengths and frequencies, and it would correspond frequencies and wavelengths to certain colors and stuff. This is how they did it. And it was mostly pioneered by Fraunhofer, and then there was a couple other guys that made some major contributions and picked up off of it. So when we get into later experimentation and they're like, oh, how'd they get these wavelengths and everything, and these and frequencies? How do they understand all this? Well, this is like the early backbone for how they did all that. It all started with splitting it through a prism and then looking at the colors, and then they were like, well, how precisely can we measure these colors?
Yeah, this is the guy who came up with Fraunhofer's diffraction. There's only two types of diffraction, Fresnel and Fraunhofer. And, Fresnel is like looking at your hand. Fresnel's like looking at your hand, and you can't see the individual cells in your hand because they're just too close together. Where Fraunhofer diffraction is when you're looking into infinity, and things in the distance just become merged with the sky because the angle of incidence there is beyond your limit of observation anymore.
Kind of like cars, when you see cars out in the distance and there's two lights, but they kind of get merged into one.
Mm-hmm. Yeah. Sorry, Alan.
No, you're good. You're good.
If I'm talking too much, just tell me to shut up.
No.
You're doing a really great job. And I'm thinking about, and I'm sure you've seen it, they're fascinating, the old movies or the old things where they're showing them doing some of these experiments, even now in laboratory, and reflecting them against the walls and how they measure it. It's so cool. You're doing a great job explaining it.
Thank you.
Don't feel rushed by any means, okay? Because I like to just pull the stuff apart and really open up the magnifying glass and all this stuff, So,
if you guys got time and it's not a constraint, like I'm good, because I didn't know if you guys, because this could go on for a minute. Okay, cool.
Don't put any pressure. And if there's another time we didn't cover everything today, we can always come back and talk about it another time if you're game for it, because this is really good stuff here. Cool. So, no time constraints. Okay, don't worry about it.
Cool. All right, thank you. So we have here the frequency spectrum here for electromagnetic waves, and we have the visible color spectrum here. We got gamma rays on the right, radio waves on the left. So as they're breaking down all these measurements and these wavelength and stuff, this is what they're associating their scale with for everything for electromagnetic propagation.
Now, do you think that's the end of the spectrum, or is that just the spectrum that we can measure?
Just what we could measure. It's a great question. Just what we could measure. It seems like who knows how far it goes, because when they get into things like what they're doing at CERN, where they're taking these really quick measurements of really small blips of energy, essentially they're just getting like a blip of energy from their oscilloscope. You could is a really easy way to think about it. And they're like, okay, what do we do with that now? And as we get things that could pick up more sensitive readings like that, they just start naming things, so it's like, I'm sure once it becomes more mainstream, the instrumentation used to analyze that stuff, that there'll be more stuff that they figure out for sure.
Yeah, me too. Okay, thank you.
Yeah. All right. Nope, that's all there is, and if it's not in a science book, it doesn't count. All right, so we have Henrik Hertz and Wilhelm Conrad, who also made some major contributions to the frequency spectrum there. And then we have Antony Becquerel and Marie Curie and some other people who did some work with the radio waves and all that. And that's how they mapped out this entire spectrum over the course of, like, it was started in like the, well, like late 1700s to early 1900s. And they just started knocking all this stuff out. All right. So we got wavelengths, we got light sources producing light, sunlight, starlight, incandescent lamps, electricity, etc. When a coherent beam of light hits a prism, it's split into 7 colors: red, yellow, orange, green, blue, indigo, and violet. When it's split into the spectrum and recombined, it returns to its original color. The wavelengths and the colors correspond to the measurement in meters, or nanometers, meters, etc., of the wavelength itself. So to recap, we have observed phenomenon, light beam being split into different colors. The problem or question was, is the light encoding the color, or is it in the material? The hypothesis: does the prism, is it in the prism or not the beam, or does the prism color the beam? And then we have the experiment where we're, splitting it and then recombining it to see if that's the case. And then it turns out that's not. And then your dependent variable would be your beam of light, and your independent variable would be your prisms.
It's kind of like different colored strings, all a part of a single piece of yarn.
Yep. It's exactly what it's like. All right. So conclusion. Yeah, we're good on that. All right. Now, the next experiment that they did in the early 1800s was the Arago. It's called the Arago spot. So what Arago did was he had a sphere and he had a coherent light beam, and you shoot the light beam at the sphere, the exact center of the sphere. The light beam diffracts around the sphere, recombines, and makes this pattern on the opposite side of the sphere. So this dot right here is 100% obstructed by a physical object, yet there's a dot right there. Well, how could that be possible if light was a particle? Because they were, when they were breaking all this stuff down, they didn't know if light was a wave or if it was a particle. Does it have particles in it? Who knows?
Is this like a transparent sphere?
No. This circle here is just to outline the radius of the diffraction pattern, and then like the important part of it. It's a little tiny sphere that's blocking it. It's about the same size as the one in the center, but we're not seeing that part of it. This is just what's projected behind the sphere.
Okay, yeah, I kind of got the impression that this is where the sphere is at, and we're just kind of looking through it. Is that right?
No. The sphere is like not in the frame. So.
Yeah, that's what the circle represents, and so that's kind of where it would be at. But this is as if you could see through it, but you can't really see through it. I don't know how to describe it much better than that.
Yeah. Well, except the circle isn't the size of the sphere that's blocking it. Like I said, the actual sphere is much smaller. This is just the radius of the important part of the diffraction pattern. Because out here it gets incoherent, and then right here we're looking at the fine structure of it. So it's just outlining that.
Okay. I was wondering about this, if it has any kind of implications when it comes to eclipses, because that's an interesting pattern that I've never seen on any kind of like a solar eclipse shadow on the Earth. Like, I just don't see that. And so, like, is there any kind of crossover here?
Yeah. Who knows? So they were trying to settle, okay, is light a particle or is it a wave? So when they put the sphere in front of it, if light was a particle, it would be blocked by the sphere. There would be no recombining of the waves on the other side to make this pattern in the center, to make this dot in the center. So that falsified the particle aspect of it, temporarily, right? We'll catch up to modern experiments where they, swear they found some particles somewhere in there, and we'll cover that. So that was
interesting thing, Alan, is in trade, they when you're in a trade that works with optics and you have to learn optics and optical properties, they don't talk about particles at all. Everything is wave.
Oh, no way.
So if you have to, in gemology, and then if you're making eyeglasses or anything like that, working with it, no, if I can send you the strict definitions and how the optics work, and they flat out call it a wave in physics. So it's funny how they, can pick and choose when you go into space and that, but they need to in reality, because in reality, you have to test for reality and you need the physics of reality.
Yep. Yeah, when it comes to the quantization of light, it's really only meaningful for the kinematic model to like reify like atomism, so they can do like, oh, we have elastic collisions of little tiny balls. And then the other usefulness of it would be to say that light can propagate through a vacuum as little quantized parts. But we're actually going to cover that at the end and how that's wrong too. So we're in for a real treat here. All right. So we have this, we have C here, and it equals lambda times F. And this is the wavelength times the frequency. So the wavelength would be the distance between the peaks and troughs. And then the frequency would be how fast it's vibrating per second, like number of oscillations per second. So they say that light travels at 300 million meters per second. You could think about that instead like an oscillation rate of 300 million oscillations per second rather than, a ballistic trajectory speed. So they found their relationship here with the frequency is going to times the wavelength is equal to, that propagation rate, what they call the propagation rate. So here's a diagram. Here's a bigger picture of that. So we have a direction of an accelerating particle, right? Now this would be accelerating charge to create the wavelength. So we have an electric field, and then that induces a magnetic field. Now that's induced by the charge potential that's in between this point. So we see these blue lines, and we see perpendicular to them these red lines going up. Now in between there, that would be where there's charge potential, right? And it's when it's accelerating, that's when the electric field creates the magnetic field. So it's becomes like a self-inducing loop, but that charge potential, that intersection point there, is required to produce that. All right. Okay, so now we're going to get into some observations and experiments regarding Earth's motion in the sky. So Arago, who we just learned about, was famous for the Arago spot, so showing that light was definitely a wave due to the diffraction pattern when it recombines after getting blocked by a sphere. This same gentleman here took a telescope and put it to the sky, and when he was observing starlight, he had his telescope half covered with a prism, and the idea was when the starlight intersected the half point of the telescope, he would have to make a correction angle to fully view the starlight when it hit the prism part of it, if the Earth was in motion, because the light will be traveling slower through the prism. Earth's velocity will be it'll be displaced from under it, so to speak. Well, not so to speak exactly. So you would have to tilt the telescope more, and he found that he didn't have to make a correction angle for it. So
this is a predecessor to the Michelson-Morley experiment.
Yep, predecessor to Airy's failure too. So this was before Airy. Don't have the year on here for some reason. I apologize for that, but it was in
one of
the
those
1700s.
really important ones that people should mark in their flat Earth history. Yeah, I don't know. With me, I've got like this big, huge page that's all about documenting significant events in flat Earth history, and this one right here deserves a spot on my wall there.
Yeah, we have a long timeline of like basically all these experiments that they did to try to measure Earth's motion, and yeah, we just like run through them all. That's basically what we're doing with this presentation right here. We're going to go through pretty much all of them.
Experiment again, Ergo's.
So this was just called Arago. I'll look up the exact stuff for it and after and send it to you.
Arago.
But yeah, so and before he did the prism, right? He also, using a telescope, he hypothesized that he would have to change the focal length of it every 6 months when you're traveling with or against the sun, based off of like how you're viewing the stars. So you're either traveling like with or against them. And he found that he didn't have to adjust it either. So that was like a big red flag. And then he was like, okay, well, let me do this prism thing and see if I have to change it. And then that didn't pan out. So they didn't really know what to do with that. And that was that was a huge problem for them. And then we'll get into So yeah, he did the prism thing. That didn't work out either. And now we're going to get into some measurements of light. So this would be, we got that induction rate of 300 million meters, or 300 million meters a second, right? Is it oscillating that fast? Is it traveling that fast? How do they get to this number? Is it magic? Did somebody make it up? What's going on here? So in 1849, Hippolyte Fizeau did an experiment with light where he had a coherent light source, and he was shooting it through he had a collimator, and then he was shooting it through a spinning cogwheel, and then they would hit a mirror and bounce back. Now, knowing how fast the cogwheel is spinning, you could create a pulse rate essentially with that, and you could deduce how fast light would have to be traveling to make it through the cogwheel, based off of its rotation rate, et cetera, to produce that pulse rate. So that's how they they have like mechanical measurements in the lab of this, right? Because a lot of the stories were, it's gangster. And then because a lot of the stories were told, when you look at like who measured the speed of light, we're like, oh yeah, 2 guys on a mountain with a candle. So it's like, oh, that didn't really work out. And then the other story you get is Romer, where it's like, oh yeah, Jupiter's eclipse or something, and it was off by 30%. Like, nah, dude, we got dudes in the lab with a cogwheel, bro. So
mechanical.
So yeah, so they got their good approximation, and then we'll go over Maxwell's derivation for it too. But yeah, so that's how they are like matching this induction rate with their math, right? Because they've got their established rate here, as we're going to find out when they start getting into interferometry. And it's like, how'd they get that? Well,
whether you believe in the speed of light or not, it's still worth like knowing how they came up with it.
Yeah,
that's
fundamental. 100%. And whether or not you believe it travels, or whether or not you believe it's an induction rate, it's still important, because the measurement result, like the oscillation rate, is the same conceptually, right? All the math is based off of the same thing. It's just where you're like the internalized conceptualization of it is where you start to get into like, oh yeah, and then then if it's a particle, it could be in space and stuff. It's like all that stuff is not in the lab frame, right? Not measured in the lab. So it's hugely important to understand this, and then to understand like where they're why these people are interpreting it this way, et cetera, right?
Mm-hmm.
So, absolutely. So the experiment here, we got the tooth cogwheel at a fixed rate, light bouncing back and forth at a known frequency and wavelength from the light source here, the lamp, because they were splitting those wavelengths earlier and measuring all that, so they had all that information, and they confirmed their math right on that. And then, so to move on, we're going to get into the first interferometry experiment. So this is a this is a diagram of what it looks like, a simplified version. But what they had was starlight hitting a beam splitter, and then it would go through tubes where the beam would go with or against the flow of moving water. And then it would be recombined by another beam splitter at the end. And then it would produce a fringe pattern. So there would be, if the light was in phase, there would be no fringe pattern. If it's out of phase, there's going to be little gaps in between here. So this is where you would see those gaps. So what they found was that, they knew about how light would slow down and water refraction rates and all that. So they knew it was going to lose, like they knew the refraction index of water. And actually, while the water's stationary just in the tube, you could measure the, you would have to have the beam split through, like one tube would have water, the other tube would have air, and then you could measure the fringe and the displacement there, and you could measure like the exact impedance that water would have on the speed of light, because you already know how fast it goes in air, right?
Okay,
so now
slow down. Okay,
yep.
So as I understand it, the refraction index itself is based on the speed of light in a vacuum, and they're trying to measure the speed of light by talking about the refraction index, which depends on the speed of light. How do you measure the speed of light if you already are claiming to know the speed of light? I don't know. That's kind of like, it feels like there's a little bit of circular reasoning going on here.
Yeah, so they had the rate of induction from like the 1800s from Faraday and Maxwell. Well, Maxwell put the math to Faraday's work, but they already had that induction rate for the math. And they experimentally did this in 1849 with Fizeau with the cogwheel and stuff, and found that induction rate was satisfactory. So they had the induction rate of light to make these determinations.
So they're basing their speed of light off of this prior experiment and saying, okay, we're going to try and match this up with that one to see how do the compare and contrast, see how they're different.
Yep. And this is why it's so important to go through the history of this, because when we get to Michelson-Morley, right? If you don't know anything about Michelson-Morley and you're just hearing about it, you're like, why would they do that in the first place? What was the purpose of that? Is that even real? But like we're like this science, this is like the history of the exactness of what they measured and like how they had like a solid foundation for this. So when we get to Michelson-Morley, they knew exactly what they were doing and what the outcome should be based off of the heliocentric model, etc. Because this is very precise measurements.
I like seeing this because I'm obsessed with diagramming the foundation blocks to a complex concept. And when it comes to Michelson-Morley, so many people, myself included, forever have thought Michelson-Morley was kind of a foundational thing, which I guess it is, but there's other building blocks that come before him. And I never quite was aware of that. So yeah, thank you for sharing this. This is really good for me.
Yeah, dude, this was all new to me too when I first, because obviously we heard about Michelson-Morley first, and then you get the history of this, and you're like, oh dang, this is like the craziest, right? Because this is like we're always looking for, as when we come into flat Earth, we're like, all right, we're doing a full reset on science. Where's your IVDV? What are you doing here? Is this a man-made device? Like, what's going on? What are we doing? So we're looking at men with cogwheels and fire light sources, lamps. We're looking at sunlight and water and crystals that are splitting beams. So natural science, like nothing crazy yet, right? So this is like the foundations of which this is all built upon couldn't be any more solid, right? Like you can't get any more natural than sunlight, a crystal rock, and water. So with that said, they knew how much how much light would slow down with the water when it's stationary. And then when they have moving water, what they found was that there was a displacement in the fringes outside of the confines of the slowing down of the water from the refractive index, but it was actually carrying 44% of the velocity of the water going with and against the the light beam. So what that means is it carries 44% of 88% total of the translational speed of the water. So the hypothesis to this experiment was that that electromagnetic waves propagate through a stationary medium, that when there's a moving medium, the stationary medium gets carried through it, and that will increase the propagation rate of light. Now, what they showed there is that there is definitely a material medium for electromagnetic waves, and that when it interacts with a moving material medium, there's that translational speed is added to it, and was precisely measured with interferometry in these fringe patterns.
Okay, so I'm kind of trying to retrace the steps here a little bit. First, you talked about Ergo's prism, and this one is called for.
So this is Fresnel. This is Fresnel. The experiment was proposed by Fresnel, and the math was derived by Fresnel, and then Fazal did the experiment.
Oh,
so a different guy, but it's called it's called Fresnel drag, but it was done by Fazal.
Or Fresnel drag.
Mm-hmm.
I'm thinking about Fresnel magnifying glasses a little bit. Guys, probably done by the same person. I don't know.
Yep. So to recap here, the hypothesis: will the translational speed of the water increase the velocity of electromagnetic propagation? And the mechanism for that, of course, would be that electromagnetic propagation has a material medium that it's propagating through. And then the independent variable would be the velocity of the water plus the refractive index of the water. Sorry, and then the dV would be the recorded fringe pattern. All right. Cool. And then we have Maxwell's induction rate. So we have nu equals 1 over the square of epsilon naught times mu naught equals C. So when we talk about the speed of light and all that, when we talk about C, this is what it's describing. And what this is describing, what nu is, this V here, is a vibration that describes vibration rate. And because there's no time component here, this is set by default to 1 second. So this is how fast electromagnetic propagation will go through a vacuum. And this was determined through experiments with Faraday and then Maxwell putting it to equations to represent that. So the epsilon would be the electric permeativity in the vacuum, and then the mu would be the magnetic permeability in the vacuum, and then that will allow for the oscillation rate of 300 million meters a second, or 300 million oscillations per second. Sorry. So that's what that looks like.
That is fast.
Yeah. Yep.
V is volts, velocity, and this new one, vibration.
Yeah, so this one's actually not a V, it's a nu, N-U.
Oh.
Yep.
Wow. Okay, I didn't know that.
Yep. And then it looks like a V, but it's new.
Yeah, the little line off to the left. Yeah, I won't even get into all the little symbols that they have for all their stuff.
It's been fascinating learning an entirely new language.
I hear you.
Lots of fun. So we have cool story, but hasn't the ether been falsified, right? So only through the mathematical reification of unsubstantiated terms in electromagnetic theory, like Maxwell's electromagnetic displacement, Maxwell's displacement current term, which is earlier we were talking about how there needs to be a charge to be accelerating for the electric field to be able to induce a magnetic field. Well, there's a term that was added to Maxwell's field equations that describe electromagnetic waves and all that. And that term is basically saying that there doesn't need to be a charge potential there, and that the electric field will just self-induce the magnetic field, even though that's never been experimentally verified. That's just what they go with to not have to conceptualize an ether for a background. And that's what they teach people about how like radio waves and stuff work nowadays.
Yeah,
so
we can't make up the ionosphere. That's what they did.
Yep. They just lie. They just cover things up and, come up with a math term to explain it. It's like, all right, just an unsubstantiated math term. So this, so back to this equation that was derived by Maxwell and Faraday. These were, they knew that there had to be an ether. They had to be a background for there to be these magnetic lines of force, to track, like, what's it forcing through? Like, what's the source of it? There was a background. Like, what's this vibration? What's vibrating? They all knew. Now they were saying, and then, the modern interpretation is no, there's no ether, blah, 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 but they're still using equations that are describing an oscillation rate through a medium.
Something has to be vibrating.
Always in an eternal, just or whatever. So
isn't that funny how it's like you look under the hood and there's the engine, and yet they close the hood and pretend like the engine isn't there. Oh, it just works.
Dude, it was fascinating looking into quantum mechanics, because it's like they've got all these particles and weights for particles and spin rates and up spins and down spins, and but we can't find it. It's a probability chance, and it's like, okay, what the heck's going on here, guys? And it's like, turns out Schrodinger came up with a wave equation that solved everything for them. And then a year later, Max Born published a paper and was like, yo, boys, if we square the solution to this wave equation, we can say that the electron is a quantized thing that exists within the solution to that squaring. And if you guys are down with that, we can roll with it. Like, it's literally what his paper says. And
all right, let's go. Cool.
That's what it's all built on. And it's just, it's crazy, dude.
Okay, so
like, when you look under the hood, you find it's just like nonsense abstraction role plays for fun.
Schrodinger's wave equation requires vibration. That's what you're saying in a nutshell.
Anything that describes a wave requires something like a medium. It's like inherent to it.
Yeah. Okay. So waves require a medium to vibrate. That's the thing here. And so, there's no light traveling through a vacuum of space, because it's just stupid, because it needs something to vibrate through.
Yeah, that's why it was such a big deal to push forward quantum mechanics and stuff. Because like I'm going to cover double slit and quantum eraser and the Compton scattering at the end. because these are the things that are put forward to make this. Oh, this vibration is just some sort of abstraction. There's nothing vibrating. It's all proportional to the quantization, which is the particle part of it. When they use E equals hv, so they take Planck's constant and then they multiply it by this vibration rate, right? This nu here, this v, or the thing that looks like a v. They multiply Planck's constant by that, and they're like, this is the quantization of light. And Planck's constant is just how much energy can exist over a 1 second period of time, which is what he used to solve the black body curve back in the, what was it, like 1901, something like that, 1902. So it's just they just applied that, and then Einstein was like, oh yeah, if we do that, that's the photon, the quantization of that's literally where it all comes from. And then it's backed up through double slit, quantum erasure, which like aren't really good experiments for it, but it's like primarily supported by the Compton scattering, which we'll get to at the end. It's really fascinating what they did there. Sorry for the long detraction there.
No worries.
It's good to chew food. It's good to chew your food. So yeah, don't worry about it at all. I need this to write my notes down.
Cool. All right. So we have here our naturally observed phenomenon of light always seeming to behave like a wave. We have first order measurements and experiments of that behavior. We have the measured induction rate of the lowest amount of physical with the lowest amount of physical material that can be measured in a vacuum to give us that epsilon naught and mu naught for Maxwell's equations to describe what Faraday was measuring. And then we have the historical theoretical framework of ether. So the way that they conceptualized the ether real quick is that they conceptualized it as being stationary and that the earth moved through it. And then this was because if there was going to be any motion to be detected through further experimentation, as we're going to go through here, any velocity detected was going to be attributed to the Earth's motion. And then you look at the modern interpretation of these experiments, they say that they failed to detect the ether. Well, what would an ether detection look like in these experiments? It wouldn't look like a jar of ether or like, I got some ether in my pocket. Do you need some? Or anything like that. It would look like the fringe patterns would show a displacement that would correspond to the velocity of the Earth moving at 30 kilometers a second. It wouldn't be like some material
something you can go collect. Yeah. It doesn't work that way.
Yeah, so it's like a marketing flip to say that it was a failure to detect the ether when really it was a failure to detect Earth's orbital velocity, because none of this you can't get rid of the medium in this. It's literally all about Earth's velocity, because all these people, as we're going to find out, we're in the Royal Society. They're all Copernican lads, so they're all going to get together and interpret things through the Copernican principle, right? So that's why all their experiments are presented in that way. That's why none of them are like in their papers. That's why none of them go, oh, you know what? And the other option is the Earth's stationary and not moving. They just kind of keep that under the wraps. They'll just abruptly, end the paper or something. They won't like really touch on it. So
real quick, Alan,
Mm-hmm.
I got to say hello to Miss Karen B. Happy birthday to you, Karen.
Happy birthday!
Thank you. Thank you very much.
Did you have a good dinner?
Yes, it was wonderful.
Wonderful.
Mm-hmm.
Make sure you tell Ted I said, good job, man.
I will.
All right. Take it away, Alan. Sorry about that.
Thank you, sir. Happy birthday, Karen.
Thank you very much. I've been listening the whole time. I'm enjoying this. Keep going.
Nice. All right. So here we go. We got first order measurements of light behaving like a wave. And we know that we need a medium for the wave because we're doing philosophical realism. We're not saying, okay, well, maybe it's a particle, or like not at this point anyway, because we're going to cover that. But moving forward, wave, medium, stationary Earth. All right. So let's look at some. So now that we got an ether model, right? We know that there's measurements of an ether through interferometry, but let's look at a model for the ether and see if we can't come up with something so that we can interpret how the ether is behaving, right? So let's come up with some a model to interpret it. So we're going to use Atutovsky's ether dynamics model. This is a It's modeled out by Atsutovsky, a Russian guy from like the 2000s. He published a book called Ether Dynamics. He basically goes over all the interferometry experimentation and a bunch of other stuff, reinterpretations of quantum experiments, etc. Where they've measured XYZ, and he wraps that up into an ether model. And we're going to look at like a broad overview of what it would look like if the Earth is stationary and there's an ether wind, meaning that the sky is in motion, and it's translating an ether wind down to us that we're measuring down here on the ground. So we're going to see what that would look like as a model. So there would be an anisotropy effect in the speed of light, meaning that if you shoot light going east, it's going to be a different speed than when it's going west. It won't be the same. So the velocity of electromagnetic propagation depends on the radiation direction, or on the direction that it's stipulated by the relative motion of the solar system and the ether, the medium responsible for electromagnetic wave propagation. So again, directionality. So you'll have a beam, you'll shoot it north, south, east, west, and you'll measure the speed, see how, and if there's variation in it, that'll correspond to the anisotropy effect of our model, right? So that'll show that there's a flow, and that you're traveling with and against the flow will either retard the light or it'll make it go faster.
As far as the color changes you do get in the light and the visible spectrum, we have demonstrated that many times on GLOBEBUSTERS Tech. You've seen us do it with mica and with cellophane tape, Karen. This is what he is talking about, the effect that we've again demonstrated, and it's just putting it, what we saw was the visible part of the spectrum of it, but what it does with the visible, it does with the invisible as well. So for those that remember those visuals, or if you wanted to ever see them, Alan, we made them and demoed this.
Oh, nice. Cool. Definitely check those out.
So I was going to say real quick with the ether, from my basic understanding of it was there is the ether there that's moving, creating a flow. And then there's the globe earthers who say, but they'll try to argue and say that the Michelson-Morley proved that the earth is rotating. And that's kind of the flip.
Oh, yeah.
It's either the earth is rotating or it's the ether that's moving, and everyone just says, it proved the earth, and they forgot about the ether.
Yep. Yeah, we're definitely going to get into all of those. 100%. Okay. Yep. Just building the framework for what the interpretation, what it is. No, you're good. Let's see here. So yeah, anisotropy. So it'll propagate at different speeds based off of, is it going with the flow or against the flow? And then we have the height effect. So the velocity of the propagation, like how fast that oscillation rate we were talking about earlier, is it going to increase or decrease at altitude, or is it going to stay the same? So when you do test at altitude on the current interpretation with Einstein and the globe model says that, heliocentric model says that light would be the same at all altitudes. There's no variation in it. So if there is a variation, and it's going faster and slower at altitude than it is relative to ground level, that means that the source of the causal mechanism, the source of it, is coming from the sky and not coming from a fixed point at the center of the Earth, right? So when you get into the measurements with the interferometry, like we were just touching on a little bit, they say that those measurements are with respect to the center of the Earth. So when we're talking about absolute reference frames with respect to rotation, if you go to the center of a rotating disk, right, that center point is going to be where all the rotation is relative to. That's going to be the point of origin of the rotation. So they equate that to the measurements with light. So they say that there can be a variance in the speed of light, but only with respect to rotation, because that's absolute. So, there's with that fixed frame there. Now the stipulation with that, if they're making a measurement of rotation with respect to an absolute frame, there can't be any variance at altitude. It has to be at that, it has to be the same. So if it was to increase at altitude, it would show that it's not with respect to the center of the Earth, and that's not that that the Earth rotating is the causal mechanism isn't on the table, is what it would show. So that's why it's important to break down the model of ether and like the causal mechanisms of the measurements and what's happening when we do them at altitude. So we have the space effect. So the velocity of the propagation will change its value with 1 stellar day. This is stipulated on, basically, it'll follow sidereal time is what he's saying here. So there will be fluctuations in the speed of light that correspond to sidereal time daily and yearly, right? And we'll get into the measurements of that for sure. So let's see. Now, the hydrodynamic effect will be that the velocity depends on the movement parameters of viscous gas. So what he's going to do is he's going to do an interferometer that's half shielded using a because what they found through experimentation through the early 1900s was that the interferometer readings are affected by the materials of the apparatus itself and the shielding that they use. So if they use a Fermi surface or dielectric insulators, so basically things that conduct electricity or store it, will affect how the interferometer makes its readings, like the strength that it's able to read at. So the hydrodynamic effect, what we're going to get into here is they're going to say, so suppose there's an ether wind that's going east to west, and it's all going, in a laminar flow. So if you were to have an interferometer parallel to that flow, it would be going through like a tube, through that shielded arm, and it would remain laminar. But if you turned it, and then it was, it would be turbulent. So it's perpendicular to the flow. And then when you turn it back, there will be a period where the ether inside of the tube is, bouncing around and causing causing interference in the readings. So we'll get into that. And the only thing that would explain that, right, would be as if there's a material medium that has terminal and laminar flow, and how much that's affected by the material, whether it's a Fermi surface or electric insulator.
So this is we're still talking about the luminiferous ether, not talking about like alcohol or something like that, right?
Correct.
Okay.
Correct.
Yeah. I'm just like, I've never heard of anyone capturing ether in a bottle before.
Yeah. So it goes through the bottle, but there's like, I don't know, like we'll go through it with the experiment of what they did. So like it hits resistance when it goes through material, right? Obviously slows down. And then there's a flow where it's not, where it goes through it because it's an open end for the interferometer. So the way it'll work is there'll be a time when there'll be like a flow that's, kind of trapped in there. And then as it's settling down, going from turbulent to laminar, you'll be able to make measurements corresponding to that using the equations that govern hydrodynamics, right? So like actual tubular and laminar flow of fluids and gases. He's saying that if you apply those equations to the interferometry readings, that you'll be able to show like a hydrodynamic effect in light, meaning that that what's propagating is flow. I'm sorry, that the medium itself is flowing. Does that make sense? Like a river, essentially.
It's a lot. It's a lot.
Yeah.
It does make sense. And no, I meant to do it earlier. I couldn't find my unmute button on it, but it's a perfect time to, when you say sidereal, to remind people what that is. And that's measuring time from the time a star that's directly over time takes to go around and come back around to you. So sidereal time, and one of the best things to measure things in the rotation of the stars. You'll find a lot of things done in it, but just reminding for people that don't know what that term was.
No, absolutely. Thank you for that. And yeah, so showing, and that's really important too, because like we're saying, if there's a height effect where you get closer to the sky and light becomes faster or slower based off of its directionality, then, that causal mechanism being the sky, that there should also be a fluctuation that when you plot the, like the variant, like the minimum and maximum peaks of the speed, then that should correspond to sidereal time, right? If the cause is the sky and not the Earth moving. So that's why, thank you for covering that. That's hugely important to this. All right. So any questions?
You're done. Yeah.
All right, go ahead.
Go ahead, anyone.
I was gonna say, is there any other questions on the hydrodynamic effect? Because it'll make more sense when I show the experiment of what they did. But this is just to kind of cover conceptually what they're talking about. Like there's a flow, and then we're going to take measurements being perpendicular and parallel to that flow, and that should correspond to the same equations that govern fluid dynamics.
Nice.
Okay. Okay, so to start us off here, we got James Bradley, who makes observations with his telescope. Now, the way that they say it works on the globe in the heliocentric model is that stars are really far away. The light's coming in parallel. So we got these straight lines coming down. We got our tilted globe Earth going around the sun. And they say that relative to the latitude here, you'll make observations over the course of a year where the starlight will kind of precess a little bit, about 20 arc seconds. And then, so what that means is when you have a star that's directly 90 degrees above your zenith, you have your telescope looking straight up at it, and you have to tilt it slightly. Number one, that's what James Bradley found. And then number two, within that tilt, you have to correct it over the course of a year. And if you trace out that the distance that it travels, you would be making at the 45th latitude, you'd be tracing a circle in the sky. At the North Pole, you'd be tracing an exact circle. And then like around Florida, you'd be tracing an ellipse. And then at the equator, you'd be tracing a straight line. And then as you get further out, it reverses or, evens back out symmetrically. So that's what he was saying he measured. Now, when they took that 20 arc second angle and they ratioed it against the speed of light, they get 30 kilometers a second. So they took this as evidence for the Earth moving around the sun. And they were super stoked about that because this was the first successful confirmation of any sort of relationship that they could establish with 30 kilometers a second and the Earth's motion, because the heliocentric model, the Copernican principle, all these things are dependent on a velocity of 30 kilometers a second. So when they applied Newton's equations to the sky, and they say, okay, well, we can derive Kepler's equations from Newton's and vice versa. So that means mass attracts mass. And we take the results that we got from Cavendish, apply that to the sun and the Earth, and we can reverse what the weight of the sun would be. Then they reversed engineered the whole model off of the sun. So anyway, they have all these weights and masses for everything, and then they have their proportional orbits to complete their circuits, right? To get everything to fit in their heliocentric model for the planetary motion. And everything has to have a specific speed based off of its mass attracting mass. So when they applied Newton's equations to the sky, they were saying that this is a dynamic explanation to the motion of the bodies in the sky. So earlier when we were talking about kinematics and measurements and stuff, this is all kinematics, right? This James Bradley observation, kinematics, it doesn't tell us if the Earth is moving or if the sky is moving. But what they have done so far is by applying Newton's equations to the sky, they're saying that they have a dynamic cause and effect relationship. So mass attracting mass produces a force, and that corresponds to 30 kilometers a second. And this was, so when they put this telescope to the sky and they were like, oh man, this is confirmation of our model. This is all where like the reification of all that comes in. But again, this is kinematics. This is measurements. This doesn't tell us if the sky is moving or if the Earth is rotating. So I'm sorry, if the Earth is in motion around the sun. So we'll
Kinematics
get into
is just making the observation. Dynamics is explaining why we see what we see.
Mm-hmm. So dynamics would be, okay, the Earth is in motion with the 30 kilometers a second based off the mass attracting mass force. Or another dynamic explanation would be the Earth is stationary. There's a firmament and an ether wind. The stars rotate every night to complete, to do day and night. That creates a drag over the course of the year. So we see a displacement. So like that, or you could take the Fresnel drag with the material media, and the stars in rotation are, there's just a drag from the angular momentum of the universe. Like there's different dynamics you could apply to it, but without actually being able to measure or like to go up there and like, make those measurements or something like that. It's all just, abstraction. But the way that they're presenting Newtonian dynamics to the sky, obviously they're going like full in, like this is what's what, like we weighed it and it's proportional to this other thing. So,
and when they did this, they even had to hide stuff as well, because that's not
Mm.
all that Bradley found out. He found out that the stars actually move backwards, you know, to that motion that they were recording moving forward, the 20 or what was it, 20 arc seconds, 2 arc seconds? Yeah,
20. Yep.
20. And then they
Yeah.
found out that it went back like 80 or 60 so or whatever every 4 years and reset themselves back to their original position. And they would mark that in the margin off to the side, and in the data they would mark it as a 0 that year and not
Yeah,
record
man.
the negative.
Dude, stellar parallax is one of the craziest falsifications of their model, because they've got instances, like you were saying, where the negative parallax is greater than the positive, and they'll just turn around and either zero it, or they'll say that it's positive, and then they'll derive a distance off of it. And it's like, bro, you just derived the distance off of a negative number. Like, what are you doing?
How do you do that?
Yeah,
What the
they've just been
negative
doing
distance
it.
exactly? Explain that one to
Yeah.
me.
Dude, yeah, they've just been applying physical meaninglessness to the sky, and they're like, it's proof we're moving. But it's really interesting, because when you get into Airy's failure, this is going to be like the settling of it, right? Because kinematics, like I was saying, can't tell us if it's the sky or if it's a medium in between us and the sky that's moving, translating the motion from the sky, or if it's the Earth traveling through space around the sun. Now you had to do an experiment, because this is just an empirical observation, right? So this is where we're going to get into Airy's failure, right? And I call it Airy's success now, because he successfully showed that the Earth isn't moving. Now when you Wikipedia this or try to look into it, you'll say, you know, it's branded with, oh, he failed to detect the ether. Oh yeah, he failed to detect the ether in his telescope, guys. That old story. So we'll go over the basic premise of it here, but kind of recapping on what Arago already laid out with the half-covered prism telescope. We have an empty telescope here, looking 90 degrees up. It has to have a slight correction angle to keep the starlight in the center of it, which means, okay, there's a drift. Is our motion the causal mechanism of it, or is the sky moving? How do we know? Well, if we fill a telescope with water, the light will be slowed down, and the velocity of Earth, if the Earth is in motion, will be moved out from underneath the starlight, essentially, and you'll have to correct the telescope further to keep the starlight in that center position of the telescope when you add water. Now, if you don't have to make a correction angle, that implies that the Earth is stationary and that the starlight already comes in at that angle, meaning it's just an apparent location in the sky, and it's not actually there, and you're not moving towards it or away from it. So what he found when he put the water in the telescope was that he had to correct it by 0.8 arc seconds. And for those who aren't familiar with arc seconds, if you take a protractor, look up in the sky, and you break up your field of view into 180 degrees, you look at that protractor, and you look at the distance between 1 and 2 degrees, and you break that into 60 sections, you'll have 60 arc minutes. And then if you break those arc minutes down into seconds, you'll have 60 arc seconds per arc minute. So you can break the distance between 1 and 2 degrees down to 1/3600th of a degree. So we're talking really precise measurements. Now, on typical ordinary viewing nights, you can see 2 to 3 arc seconds, and sometimes you can see 1 arc second, but never any more precise than that, because the atmosphere is basically an ocean of air, and good luck getting anything more precise than that. It doesn't matter how, for terrestrial observations anyway, it doesn't matter how good your optics or aperture is. That's all you're going to get. So what they said is that, and now the prediction was that they had to correct the telescope by 15 arc seconds over the course of a year. 6 months, they would have to correct it by 15 arc seconds, and then they'd have to tilt it back by 15 arc seconds, because you'll be going in the opposite direction, right? So a total of 30 arc seconds total, 1 arc second per kilometer for the velocity. So that was the prediction with respect to a stationary ether. So the Earth moving through the stationary ether is going to require a tilt of 30 arc seconds in total over the course of a year. And they found he had to move it a fraction of a fraction of a fraction of a fraction. So we're 4 fractions deep, not enough to substantiate heliocentrism. We would need to be 3 fractions deep to get that. Now,
Exactly
But
how
it,
you
now,
can kind of keep track of that over that long of a time, I think is pretty like difficult to do, especially if you got like water in there. Like, yeah, is it all contained? Like, I'm imagining dust getting out. Oh, I got to go dust it off. Oops, there. I've like, yeah. How does he keep track of all that? I
Well,
just,
these are the Astronomer Royales. They're working with they have observatories by this time, don't they? James
oh,
Bradley's time.
dude, you want to know some? You think like Tartaria, old world stuff, dude? These dudes have had observatories on observatories, and then they build observatories on top of ruined observatories. Dude, it's insane. Like, I think these guys always existed or something. It's nuts when you look at the history. There was always an observatory. It was like like if you go back to biblical history, I'm pretty sure on one of the days God was like, we're putting an observatory here too. and then there was always at least one to start us off with, for sure. So yeah, we got the measurements that don't correspond to anything meaningful for heliocentrism. And then in the paper there, he says, this is Airy, this is Astronomer Royale. He says, I think myself justified in concluding that the hypothesis of Professor Kinkerfuse is untenable. And the hypothesis again was that stationary ether, Earth moving through it, would have to correct by 15 arc seconds, 6 months out of the year, and then another 15 in the opposite direction for the other 6 months to complete 30 arc seconds. Didn't have to do that. Implication, Earth is stationary. The IVDVs of the experiment are the telescope with and without water, and the dependent variable would be the correction angle of the telescope. And so without any substantiation for heliocentrism so far, we're all waiting with bated breath to find an experiment that substantiates these velocities. All right. So went over that. Okay, so now we'll get into interferometry, right? So we went over the first interferometer experiment with Fazal, where he learned that you could measure the translational speed. You could measure velocity with light. And knowing that, they proposed in 1887, actually 1881, Michelson-Morley did their first experiment, but the apparatus was too sensitive. The configuration needed to have some tweaks to it so that they could reduce background noise. Although I did find some stuff from Lorentz and Paul Drude who said that it was that apparatus itself was accurate enough, but we're going with the 1887 one because this is supposed to be the more accurate one here. Okay, so all right. So this is a topographical, or this is a side view here of what the interferometer looks like. So we have a vat full of mercury, a giant concrete slab, and we have mirrors fixed to the top of the concrete slab. We have a collimator for a coherent beam source to send light. And then we have a telescope to look at where the light is being projected onto. It's being projected onto a screen where they're taking their measurements with. So here's a topographical view of what that looks like. So you got your light source, beam splitter, and it splits off in different directions such that it's orthogonal to itself, making that right angle. And the reason for that is that they're saying they're producing a like a circuit, essentially a closed circuit where they can have light going with and against the direction of motion, or with and perpendicular to it. So it will be the light that's perpendicular to the direction of motion will be retarded as it's going through dragging through the ether essentially. And that will produce a measurement of Earth's velocity, right? And that should correspond to 30 kilometers a second. So this is the topographical view. And the reason for having it bounce back and recombined is to extend the distance of it so that they can increase the accuracy of it. So you need the bigger the distance, the more sensitive you can get, the more reading, the more sensitive you can make it to get readings, right? But there's a trade-off with how long you make it, and all that stuff. So what they found was that I think this one was 64 meters or something like that. Let me check. Doesn't say in the next slide. I think it was like 64 meters. Anyway, that's the reason for the bouncing back. Now they say that this is a second order experiment, but we'll get into that here in a minute. Okay, so here's the math from the paper. So we have V for the velocity of light, V for the velocity of Earth. We got the T for the time and D for the distance. Now, after doing some higher order approximations to determine if they needed to account for the fact that the Earth would be moving through space, and essentially it would be in a different location from when it's bouncing back in between the mirrors. So is that effectively going to change the actual physical d, the distance of the apparatus? And if that is something they need to account for, and what they found is that they didn't need to account for that, it would be negligible. So they just use the actual device of the apparatus. So what they do to represent that, they do 2d times v squared over c squared, right? Well, it's a v and another v, or nu and v over there. But anyway, that's what it's representing here. So it's just the distance of the length of the apparatus times the expected velocity over the speed of light, and that will give them their ratio for their expected fringe pattern. So they put 30 kilometers a second in here, and then when you solve that, that gives you how much fringe is expected based off of that velocity. Okay, similar to how they were deriving it with the water.
This is just more fine-tuned, right?
Yep. And actually, what's cool about this is this equation here is the same equation that they used in modern gyroscopes, so inertial navigation systems. This isn't like, oh, this experiment didn't work out and this was wrong or X, Y. Nope, this was spot on, dead accurate, because this is what they used to derive the Sagnac effect. I don't know why I air quoted that. This is why they, this is the exact equation that they use to derive that stuff now to this day. So they had it properly figured out and understood back then. So hypothesis: the Earth is in motion when the interferometer is aligned in, or perpendicular and parallel to that direction of motion. There will be a proportional velocity that they can measure. The independent variables would be the wavelength of light, the orientation of the interferometer with respect to time. So you're going to be making measurements at different times of the day and year, ideally, right? Because you're in an elliptical orbit, so you're going to be changing speeds. So ideally, another variable that would be with respect to the time of year. But in this case, it was just respect to the time of day. So they took measurements at 6 a.m. and 12 a.m. For their sidereal measurements. And then the dependent variable, of course, would be the fringe pattern that they measured. And what did they get? They expected, solving this math right here gave them 0.05 of a fringe for it to correspond to 30 kilometers a second. And what they actually measured was just over one fringe. So they measured 5 to 6 kilometers a second and not 30 kilometers a second. So that's why, all the physics had to be redefined after all of that, because they knew and understood that the significance of this, because they already knew you could measure translational velocity with it. They already knew you could do this. So if there's a medium and we're moving through it, well, you could definitely use a sensitive enough interferometer with enough distance to pick out that velocity. So it's unfortunate for them that didn't happen. And then to give some explanation here, it's not showing that slide. Oh no, it is. I'm sorry. It's at the bottom. I couldn't tell on my end if that was showing correct. Okay. So some people will say that this falsified the ether, et cetera, et cetera. Well, that's not what happened at all at the bottom here. We can read the conclusion. So what Michelson is saying is that if the Earth is in motion, it must be, going really slow. And maybe we should take some observations at different times of the year to see if we can figure out if there's a fluctuation, or we can plot that against, sidereal time and see, if it corresponds to the space effect, right? What we were talking about earlier with how when you plot these, the minimum, see how these, when you look at this, it goes up and down a little bit. There's a fluctuation here. So what they would be doing is taking measurements over, over the equinoxes, essentially, right? Where you would have minimum and maximum speeds, and you would look for fluctuations, and then daily you would look for fluctuations within that too. And that would, and when you plot those against sidereal time, if those correspond to, sidereal events, well, then you would have your causal mechanism of what's going on, of what you're measuring, right? So, all right. So the reason all the physics had to be redefined over that is because they didn't get the measurement that they needed. So Einstein was able to step in with his explanation of length contraction and time dilation and reference frames and all that. So what Einstein says in his 1905 paper is that there's no ether, there's no need for an ether, guys. There's no need for a preferred frame. So so mathematically, the ether would also serve as a preferred frame where you could, or where motion would be analyzed, where everything would be relative to that. You could conceptualize it like that. So in this equation here, the V over C squared, the ether, like the ether in this equation would be the C squared, because the measurement of velocity is with respect to is with respect to C. So it has its own. Your mic is on point. Okay, so you the measurements would be with respect to that frame, right? So Einstein is saying that that frame doesn't exist, and electromagnetic propagation just goes through nothing, and that any inertial frame is as good as any other.
It's important to remember, though, that Nikola Tesla was around in that day too, but he disagreed with Einstein, and he very much believed in the ether.
Yep. Shout out to Tesla, dude. True homie. So Einstein puts forward these postulates, right? No ether, no preferred frame, and light, and because of that, light propagates at a fixed speed. So the conclusion to this, to the Michelson-Morley for the heliocentric interpretation, is that they measured nothing, right? They just measured instrumental air, and that the speed of light is the same. And then from that, Einstein's going, okay, bet. So if we take that interpretation, we could say, we can use reference frames to explain this. We can use kinematic principles. We can say that no reference frame is as good as any other, which is true in kinematics, right? Relative motion is true in kinematic analysis, but in reality, right, with the car and the hitchhiker, we can determine, which frame is in motion and not. So this is what he's putting forward for everything. And then we won't have to assign imaginary velocity vectors where electromagnetic propagation once took place in space. So when we get into rotating interferometers and stuff later, they'll say that the distance is changing, and it's like, well, that's true, but it's changing with respect to absolute space. And Einstein is saying here that he could answer an interferometer without invoking absolute space, which can't be done, because if the speed of light is going the same irrespective of absolute space, then the effective length of this apparatus as it's turning wouldn't matter, and the beams would recombine at the same time, and it wouldn't produce a fringe. So there's a huge problem here, which we'll get into a little later. But basically, the fundamentals here are no preferred frame, C has a fixed speed, and they don't have to assign imaginary vectors to use absolute space to explain anything. And he says further, where do his equations apply, which is really important. So he's pointing out here that his equations hold true for any closed polygonal circuit in uniform rotation by the analogy given. And what that means is if you have, we'll look at a Sagnac device. So this configuration here is known as a Michelson-Morley style, or an orthogonal setup where it's split at a right angle. And then here we have a closed loop circuit that goes clockwise and counterclockwise and recombines at a detector. So when this is in rotation, they say that, that the effective length changes, but it's with respect to absolute space. But anyway, Einstein's saying here that, it's not the case, whatever. Now, if he says that, though, the speed of light would have to be the same, and there couldn't be a fringe shift pattern produced. So in 1913, when Sagnac came along with a uniformly rotating interferometer, the exact conditions Einstein was talking about where his equations would hold true, he found that the speed of light is different going with and against the rotation of the device, and that's proportional exactly to the rotation of the device, or of the table, right? So the equation here looks the formalism's a little young, so it looks a little confusing, but it's the same exact thing here, and I'll show a better one at the end where it's less confusing. But essentially, it's just the angular rotation of the device, 4 pi times the angular rotation, and then the over C, which gives them their fringe, right? I'm sorry, yeah. So the angular rotation of the device. So that's what gives them their fringes for everything, and that's why Sagnac was like, "Hey, I falsified Einstein and found the luminiferous ether," right? And then they had to make another. They had to redefine Einstein's explanation for the Sagnac effect too, and say that special relativity doesn't apply to it because it's a rotating device. It's actually an acceleration, so we have to use general relativity. But we'll it's not really the purpose here to get into the full extent of that. It's just the fact that there's motion here, and it's being measured relative to an ether. And sorry if you can hear that in the background. Another important thing to note is on this uniform rotation, right? Why this is important. So Einstein says his equations hold true where if you're in uniform linear motion, right? So if you're traveling in a straight line at a constant velocity, you're going to measure the speed of light being the same, and you can't tell if you're moving, right? So if the Earth is moving around the sun, you can't measure it because the speed's pretty much the same, blah, 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 right? Because it's just a big circle. If you extend a big circle out to infinity, it's essentially a straight line. So that's Einstein's logic for saying his equations would apply in a uniformly rotating circle. Now, this is
infinity,
right? Well, I mean, conceptually, it tracks, right? But the problem is the problem with that is if you apply that to this, the smaller version, right, at a slower speed,
comes right back around. Yeah.
It shouldn't produce a measurement of the velocity of the table. So like, yeah, it's devastating for that. So because if you take any portion of this rotating device, it would do the same. It would, same thing. So he gets owned by his own logic. All right. So the IV in this is the angular velocity of the rotating device. The dependent variable again is the fringe, and for the math, it's a first order analysis because it's V over C. There's no squaring or anything like that. All right, so this is just Sagnac going into detail on what he measured. So he calls it an optical vortex within the rotation. So he's saying that there's an overall ether wind, right? And if you could equate that to like an atmosphere, and then within the atmosphere, there's winds going in different directions. So that's what his conception of it was, is that there's an ether, and that within that, there's ether winds that's relative to some velocity. So like if the way that it's measured out through interferometry, because they say you can't measure linear velocity, but we're going to go over an experiment that directly contradicts that. But the way I conceptualize it is that any velocity, linear or rotational, produces like an ether wind around that observer. And when light is coming to you, you measure it retarded proportional to that ether wind that you've created around yourself with that velocity. And then you would get into like how precisely you could measure that versus how fast you would have to be moving to get the noticeable effect. But that's where I'm at with it, because you could measure it like 1-to-1. So that's what he was putting forward. And turbulent air. So
wow.
So yeah.
Hold on one second, Alan. Big shout out to Mike Jones. Says Alan is a true homie Tesla OG bucket lad. Much love, brother. Thank you.
Dude, a bucket lad. That's what's up.
Good stuff.
Yeah. So yeah, he's saying, so Sagnac's early conception here was that, turbulent air was produced by the rotating interferometer. So essentially the optical vortex would be a turbulent flow within the laminar flow of the ether wind as he was conceptualizing it. All right. Let's see. So yeah, just reiterating where Einstein says his equations apply to, fully explain why it's falsified in that regard. Now, it gets into a significant problem for their interpretation here of motion and light and all this regarding that experiment, because, he's saying right there that the speed of light has to be the same, and then it's measured not doing that. So here's a list of, over the course of the last 100 years, here's 21 lads trying to explain this effect as a consequence of relativity. And they can't do it because, again, if you can't invoke absolute space to change the path length to, explain the measurement, then the speed of light would just recombine and there would be no fringe pattern. You would not be able to measure it it would just produce a solid line when it recombines. It would be in phase. There would be no gaps for them to measure. Like the fringes, those are the gaps that that's produced when the light beams recombined. There would be none of those if
Yeah, we
relativity
wouldn't have
was true.
wavelengths of light.
Yep, precisely. And so here's 40. I'm sorry. Here's 20 lads trying to figure it out, and then one of which in here is Paul Lavue, who comes in and says, "Well, we have to use general relativity because it's in rotation. We have to treat it as an acceleration. It's different from linear motion in the sense of a straight line." Blah blah blah. So they say, okay, we'll invoke a geometrically convenient position. We'll get at the center of the device, and we'll use general relativity math. So at this point in general relativity, they're using metric tensors for the conservation laws. So on the small scale, they can one-to-one swoop up the conservation of the rotation of the device, turn that into a gravitational field, and say that that's equivalent, that the strength of that field produced by the rotation would cause link contraction and time dilation on the small scale to explain that phenomenon within the apparatus so that they could have their gaps. But that's obviously preposterous, and they abandoned that explanation, and they don't really talk about that anymore, and they just teach it as a relativistic effect as a time displacement, and they still invoke the geometrically convenient position at the center of the device.
So that answers this question right here, doesn't it?
What's that?
Do you
What's
see
the
it
question?
up? Did Michelson-Morley bring in the interferometer from an outside reference frame? If it was always on Earth, why did it contract more?
No, it's always ever been done on the Earth. So in contraction's never been measured. So to get into that real quick, relativity theory is based off of second order effects that are supposed to be measured in velocity, which are link contraction and time dilation. So you would have to have some measured velocity, and then you would have a difference between that velocity and an inertial observer would be link contraction and time dilation. So the fact that they did the interferometry, the Michelson-Morley experiment, and they say that they got no fringe reading, and then on the back end of that, they can reverse like when you apply relativity to it, you're just saying, hey, we have this second order effect here that we can say our device would have measured the velocity, but because we're traveling at relativistic speeds, we got to use a Lorentz transformation, and that means that the apparatus is physically contracted and time is dilated in our reference frame, so we can't measure it. So it's just like, yeah, it's the ultimate reification. Like they've never actually measured link contraction or time dilation or anything to substantiate the principle of relative simultaneity, which is that observers in motion will make different measurements relative to other observers in stationary or moving, right? So like they'll all produce different measurements based off of their velocities, and that's never been substantiated. And actually GPS directly contradicts that on the face of it because it's all synced to a cohesive timeline. But just conceptually for like what they're saying is like, oh, we didn't get the velocity. So what must have happened is these second order effects of link contraction and time dilation. Hopefully that answers it.
The absolute reference frame, we're talking about inertial reference frames, which are non-accelerating reference frames. And so one of the big things that come up with here is, does that make Newton a geocentrist? But
yeah,
as I understand it, it's non-accelerating, so the Earth could still be, according to Newton, still be moving around the sun, so long as it's not accelerating, because speed itself is not an acceleration.
So Newton at the end of his Principia, what was found, I forget the gentleman's name, but this is published in Robert Sangenis's and Robert Bennett's book, Galilean. The church was wrong and Galileo was right. Or I'm sorry, the church was right and Galileo was wrong. My bad. Anyway, he goes over exactly what you just talked about. And it just escaped me. What was it again? It was, Newton's philosophy on geocentrism. So he did write at the end of one of his Principias that there was an ether and that that it was possible that the Earth would be stationary. Yeah. That was taken out.
End of Principia. He says he claims geocentrism.
That's what is put forward in the writings that were removed, and then like I said, some guy, you know,
They took
some researcher.
out of Principia.
What's that?
They took stuff out of Principia.
Well, yeah, he
Yeah.
wasn't alive when they had actually published it.
It kind
had
of
already
like sounds
died.
like missing books of the Bible. They're like, oh, we don't really like this one, so we're going to take that out and keep all this stuff in.
Oh yeah, dude.
But
Dude, they
originally,
found.
he claimed geocentrism, and then they just like, we don't like that, so we're going to take it out.
Dude, they found Galileo or Copernicus also had some hidden writings where they walked it all back. And like Galileo wrote some dude before he died and was like, yeah, bro, they could never work. It's crazy what, if that stuff's true or whatnot. But anyway, yeah, there's a whole book on it. It's all cited in that book. So,
Real
definitely
quick,
check it out.
before you continue, big shout out to Leland Wilt over on Rockfin. Says much love, y'all. Much love, to
Dude.
everyone. Thank you.
I'm going
Shout
to
out
look
to
into
Leland,
this one
dude.
on End of Principia and kind of, yeah.
Yeah,
You got any breadcrumbs for me to follow up on that one? Because that one's like a really hot topic for me right now.
Oh yeah, dude. I'll upload a bunch of sources for this on EtherCause, and I'll have a link for you. You could download the PDFs, check them out.
I appreciate
Because yeah, the stuff that they took out of the Principia and the Kepler and the Copernicus and Galilean stuff that's removed. It's like, oh, okay, well, if that's big if true, right, or whatever kind of thing.
Yeah.
It's like, oh, they just walked it all back before they died. Cool.
Yeah, one of the big things I've just recently discovered in Principia was Newton claimed that inertia was a force. I was like, that is fascinating. Yeah, big consequences right there, but I don't want to sidetrack you.
No, you're good. You're good. All right. So let's see. So general relativity gave a explanation that was pretty crazy and no one really liked it. And they had to simplify it by just saying like, just trust us. It's a relativistic effect, even though it's not, right? Because relativity is a theory of second order effects, time dilation, length contraction. And what we have here, the Sagnac effect, this velocity effect, the velocity is a first order effect. It's a classical effect. It's not second order, right? So you can't say that a consequence of the rotating device is an effect of a consequence of relativity. That's R worded, as they say on the streets. So I think we can move on from that one now. I think we got that. So just to kind of reiterate there, yeah, we're gonna move on by reiterating. so the time in the lab frame and the time on the spinning apparatus in the distance is the same, right? So the only way that this measurement could be produced is if it's with respect to absolute space. And this is the whole conundrum that all these gentlemen couldn't solve anything with. So that's unfortunate for them. So that's just what this guy is pointing out in his paper here. And this guy goes on to say in 1926, Pogne, he says, with the velocity is about 20 meters a second, the ratio would be 30 million. So what he's saying here is that for a spinning device at, because relativity is at like relativistic speeds, right? So like near the speed of light, super fast stuff, right? An interferometer sitting on a desk spinning with a rotor is not relativistic speeds. And he's saying to invoke relativity as an explanation for this, the device would have to be spinning 30 million times faster.
Yeah,
that's unfortunate.
Yeah,
that's unfortunate. It's unfortunate. And then here's what it looks like graphically, like on a graph when they explain length contraction and time dilation. So we have this center point here going straight up. So this would be an inertial observer. He's experiencing proper time and proper length in his frame because he's not doing anything. And in relativity, proper time and proper distance is relative to the inertial frame that's being used. So it's not like he's not invoking it as an absolute. So it's a little misleading with the proper. But anyway, so inertial lad's got a straight line, and then the curved line, I'm sorry, the deviation from that would be the observer over here. And that's represented by his velocity, right? So how fast he's moving at relativistic speeds, he's going to experience length contraction and time dilation relative to the inertial lad. And that divergence looks like this. If you were to plot it out with what do you call it? Hyperbolic lines here, you would see like it's hyperbolic contraction and hyperbolic dilation. So that's what it looks like on a graph. It's just that geometrically convenient position. So this would be an observer at the center of a rotating device, and then at the rim of it would be the divergence in time and distance that would be explained. So what they're doing to explain this is they're doing what's called a Lorentz transformation, and they're giving you this nice cool graph here that explains this without invoking absolute space, but it actually doesn't because, like I said, it can't, because the speed of light would just be the same in both directions. There wouldn't be any divergence. So, and this is from a paper from 2015, trying to explain the Sagnac effect in pure geometry, and in an experiment from Ruyang Wang, where he uses a linearly configured gyroscope to measure linear motion. What do you know? And then we have a paper from Barrett 2022, a quest for the origins of the Sagnac effect. So to this day, to modern times, right? This is millions and billions of, I'm sorry, that's the wrong scale. This is hundreds of years later, where they still can't explain the Sagnac effect as a relativistic effect. And we still got some lads trying. Shout out to the boys. Now, what Barda and Tartiglia end up saying is that, I'm just going to breeze through this because I've been talking about it and we've already covered it pretty much. So I'm just going to breeze through the slides here. These are just excerpts from their paper where they're saying, oh, this, we can't explain it. It's super explainable with classical effects. And then when we get to relativity, oops, really, really hard. And by really hard, we mean impossible, because again, it wouldn't produce a fringe. So they do these thought experiments to explain actual experiments, and none of them, and then they go, we satisfied the conditions, and they pat themselves on the back, but they didn't, because there's still a fringe pattern that's measured. So, and then, so we'll wrap up on the regular rotating interferometer device, and we'll get into the Michelson-Gale Pearson experiment, right? Remember that time they said they measured Earth rotation, Earth ball go rotate?
Mm-hmm.
You guys remember that classic?
Oh yeah,
so
that was a big one.
So instead of having a rotating interferometer on a table, we have a interferometer built into the ground over, I think it was about like a kilometer or two big. And what they're doing there, the same closed loop circuit recombines, and they're going to plot these measurements against sidereal time to see if there is a fluctuate, or see if that corresponds to motion. Now, at this point, they say, hey, bro, you can't measure translational speed, right? So we're not going to derive any velocity from this. We're going to be looking at it for angular rotation. So the translational speed, don't worry about that. Just look for the angular rotation, and then we'll plot that to the sky. And if it matches, we'll, good for us. So here's a topographical view of what that apparatus looks like. So it's just, you got the light going in. It's a beam splitter, goes in opposite directions to itself, recombines over here, and then they make their measurements. All right, so this is a first order setup, clockwise and counterclockwise, circle beam recombines in the loop. Now we got the math for it here, and they're doing, so they say here that this is done with the hypothesis of a stationary ether, well, how they derived it. So anyway, they're saying they derived it using the Earth rotating in a fixed ether. So the Earth's rotating through the ether, and they get their derivation here. So this looks similar to what we were looking at earlier with the Michelson-Morley, right? We have the pipe going east-west, or the counterclockwise and clockwise beams. So this is what they're representing here with that equation. And they say that relative to the lattice, right, because they got their rotating globe, or on a plane, we would have a vortex in the center, and as you get further away, the increased velocity to maintain that speed would produce the same effect relative to the lattice. So what they're saying here is that the fringe displacement relative to the lattice will this is the equation for it, right? And that will give them their angular rotation rate for the Earth, and then they'll apply that to sidereal time, and they'll go, okay, we got fluctuations here and here. Actually, I wish I had the plot points that they for their data so you could see it, but basically they were just plotting the min and max of the fringes, because remember, they're not concerned with the getting an actual velocity out of this. They're just looking for plotting them the peaks of the measurement against sidereal time. So when they did that, they said, oh, well, it matches within 98% of sidereal time. So, Earth rotation, boys, we measured it. Now, we're going to get into the follow-up experiments to this and to the Michelson-Morley experiment. Because remember, Michelson was saying, hey, we should take measurements throughout the year at different times of the month, basically on the equinoxes to see what exactly it is we're measuring. So we're going to look at what was picked up by Dayton Miller here in a second. But to recap here, so the IV of the experiment is the orientation of the tubes relative to the time of day it's measured, right? So we're taking measurements when the Earth is supposed to be, rotating with respect to the stars. So they're saying that the fluctuations based on the time of day will correspond to us being able to measure that. And then the dV again would be the fringes. And the result was that it produced a proportional velocity proportional angular velocity of 15 degrees per hour. And from that, now again, we're looking at kinematics here, right? This is a measurement, right? It doesn't tell us if the sky is moving or if the Earth is moving. So we're still in that. So we have Dayton Miller coming up next. So 1887 was Michelson-Morley. And then from 1902 to 1933, Dayton Miller continued the Michelson-Morley work.
What a stud.
Dude, absolute boss, bro. And he owned a flute. He was a master acoustician. He very well understood waves, vibrations, and mechanics. And when he got down to business with this work, he really honed he did 30 years of experimentation, and like a good 10, 15 years of that was like honing in what exactly he was measuring. So earlier I was talking about Fermi surfaces and dielectric insulators, and it's like, what is that? Where does that come from? It comes from this man right here, using different materials, shieldings for the apparatus, different
30 years. Now, I know you can't even imagine that, Alan, but I mean, I can't even imagine it, and I'm old.
He dedicated his life to it.
Experimenting, and it wasn't like one a day either.
No, it was.
He did millions of these tests.
He did hundreds of thousands of them, and then that corresponds to like millions of measurements because of the
millions
way
of
that
measurements. Yeah.
Okay. Yeah. So if he did 5 million something total measurements is what it would come out to. But yeah, quite an extensive load of data, and so we're gonna go over the history of his work here. So again, for the IVs, we got the orientation with respect to the time of day. And then we're going to go, and then he takes it a step further and starts measuring things at altitude. So remember, we were talking about the space effect and the height effect. So when we get closer to the sky, is the velocity that we measure going to be faster or slower, the same? Like, what's the deal? So if it's faster or slower, then the causal mechanism is an Earth rotation, right? So, and anyway, the dependent variable would be the fringes. And these are first order effects that match sidereal time. And the way that it's presented, right, is that these are second order effects, but the Sagnac effect was linearized in 2004. So from here on out, I'm just going to refer to the right angle setup, this orthogonal setup, as a first order measurement, because it turns out it doesn't matter what the configuration is. They all measure the exact same thing. All right. So 30 years, discovered, analysis, fluctuations. Cool. All right. So shout out to Dayton Miller, a true OG. All right, so this is we're going to go over some pictures of the apparatus here. So this is what it looks like. So we got spinning it could rotate. It's got the crossed arms, and then we see it with its shielding on. So in this shielding, he's using wood and glass, I think it is. And then here's the apparatus with the shielding removed. So you can see what that looks like. And then this is so he did like a large series of controlled experiments. So he had different interferometers in different locations, one of which was the Case Physics School or Case School in I'm not actually sure where that's at, but one of them was there. I think it's in California. But anyway, in this basement, what he found was that the ether, right, when you're below sea level, and when you're in it, particularly when you're in a basement, concrete, etc., all these factors reduce the measurements that you're measuring, reduces the velocity that you're measuring. So Michelson-Morley, right, was done in a basement. It was the shielding that they used was a thick wood, and yeah, actually it didn't even have glass. It was just a thick opaque wood. So they got that 5 kilometers a second velocity, right? And then Miller found that when you take it to altitude, when you do it in open air, so like in this hut that he had, it was basically designed with the least amount of like physical material that would impede it, but still being able to block thermal effects, like from the sun and whatnot. So he had this this observatory built up at Mount Wilson, and that's where he had another interferometer up there. So he would take measurements, from the control down here, figure out what's what, and how the measurements correspond to, or how they change in regards to the shielding, the materials used, etc., different heat sources. So like he would shoot heat lamps on it. He would change like all kinds of stuff with the experiment, man, and just really, really honed it in to figure out what he was measuring. So we're going to look at the measurements here now. So like Michelson was saying, we should do this at different times of day and throughout the year. So what he found is that there's a periodicity where the speed of light reaches has minimum and maximum peaks that fluctuate throughout the day that correspond to the sidereal time, and they reach their minimum and maximum dimensions on the equinoxes. So they go the slowest and fastest at certain parts of the year, which there's no mechanism for that in the heliocentric model at the velocities that are measured, right? Because they know that it's a first order measurement in velocity. So if there's a velocity that's being measured and it's not 30 kilometers a second, that means that, like, best case scenario, they would have to rescale their entire model to fit it, to make the distances fit, and to make the orbital distances fit a velocity of 30 kilometers a second, because it's all scaled proportionally. Now they could do that, but obviously they're already committed to 93 million miles, et cetera, et cetera. So that's not on the table. But that's why they ignore these measurements and whatnot, because the actual people that were like the physicists at the time all understood this relationship. Now it's not so well understood now, and people, you forgot about it, and heliocentrism is so assumed that you just, like, yeah, of course there's no ether. But they all knew exactly what was being measured here and the implications. Now Miller and Michelson and Edward Morley would host debates where they would present their findings here, Miller's findings, and they would debate anyone on relativity and ether. Now, sadly, Einstein never contributed to the debate, but yeah, they would literally, anytime anyone would critique Miller's work, he would go and do more analysis, more experiments, and he would directly address the critiques with more experiments. Because the biggest critiques put forward to explain his results is like, oh, it's a systematic error, and Miller didn't know about temperature fluctuations and blah blah blah, like all this stuff, right? Well, it's like so his work.
I'll go test it.
Yeah, he'd be like, oh, okay, I don't know about temperature. Let's go see what this radiant heat source does when I put it on top of the device, when I put it in the room. How does does my lab assistant's body temperature affect it? Like, I'm gonna have him stand, you know what I'm saying? So like he went hard on all that stuff, and we just kept measuring the same exact thing over and over again. And it was daily periodicity and annual periodicity. So to conceptualize that, when you plot that against sidereal time, Miller thought that, being a heliocentric globularist, he thought that what he was plotting was the Earth's motion around the sun. So you know how the Earth would have to change speeds and slow down corresponding to its velocity around the sun based off of the time of year. So that's what he was measuring, but just at a velocity that's not tenable for heliocentrism. So when you plot all that out based on the minimum and maximum dimensions and the time of year, like, look at what he modeled. He literally modeled the equinox of, like, because it's plotted against the equinoxes, right? So when you map it out, I mean, it would literally be, exactly what they would need to confirm their model if it had the velocities that they needed. So, and they could never
did
go
it
back
move
on it.
faster in the winter time?
Yes.
So almost like the sun had to move more distance to cover the same angular speed.
It's exactly it, bro. Oh, thank you for, yeah, it's been a minute since I've touched on that. Yes, that's exactly it. So for the analemma, right, in the north, the sun is moving at a certain speed, and then it goes out to the south. Now on a flat Earth, we're like, oh, you know, if the Earth is extended out as a plane, as a, you know, disk plane, then the south is going to be way bigger. And it's like we get this crazy analemma that's disproportional to the north side, but we still have the same, you know, 24-hour cycles. So how's that possible? Well, this.
There you go.
This exactly. So yeah, that's exactly what he measured. And so these are, again, first order measurements of the velocity in light changing with respect to the sky. And then again, at altitude, showing that these measurements aren't with respect to the center of the Earth, right? It's not with respect to a abstract conception of absolute space. It's with respect to the sky. All right. Okay. So now we're going to get into some Urey-Galev. So we were talking earlier about the hydrodynamic effect in light and what that would look like. So now we're going to get into that. So I'll read here from Galev's paper.
Before you do, I'd like to give a shout out to Rico's Tinfoil Sombrero for gifting 5 memberships here on the YouTubes. Thank you so much, brother. Much love, Rico.
Nice.
All right, Alan, take it away.
Absolutely. All right, so we have here, it says the purpose of this work is to experimentally verify the optical wave range, the hypothesis of the existence in nature of the ether, a material medium responsible for the propagation of electromagnetic waves. The second goal of this work is to measure the kinematic viscosity of the ether. Thus, the present work is a logical continuation of the studies carried out in the radio wave range. So we're going to be talking about the properties, like how, well, we'll get into the hydrodynamic effect. But yeah, so the purpose of this is to verify the existence of the material medium, right? That has to exist for electromagnetic waves to exist. And secondly, is going to measure how fast it's moving. That's quite an impressive claim there. So we'll see what he's doing here. So if we look at this, we saw some I'll show you the topographical view real quick because this one's kind of bad. So this is what we're looking at right here, a topographical view. We have an open side and a side that has a tube, right? And the closed tube section is going to be where the hydrodynamic effects are going to be measured in. Okay, so here's what the apparatus looks like. It's a plastic tube, and I think he used cardboard for the shielding because again, you want you know, the least amount of dielectric insulating material or Fermi surfaces. You want the least amount of conductivity or capacitance for storage. So he's got your boy cardboard around there. But anyway, he's got the tube and he's got an open end, and the beam hits here, goes through clockwise and counterclockwise to itself and recombines. So what he's doing here is we have a flow of ether, right? And then we have the device that's going to be orientated parallel or perpendicular to that flow. And then based off of that, when he turns it back, the optical wave bands, like what he's measuring, right? There's going to be bands of like, you know, those those gaps, they're going to be moving across the screen of the detector, right? So when the device what he's doing is when he's perpendicular to the flow and then he goes parallel to it, he's seeing how long it takes for those wave bands to become unchaotic and to produce a coherent pattern, which is where you measure your velocity, right? So what he does to do that is he applies some hydrodynamic equations, gets a little Reynolds number out there, comes up with the coefficient for how much time it would be from when it's incoherent to coherent, right? When he applies all that, and these are the same equations that you would use to, you know, do hydrodynamic calculations for the flow of you know, gas through tubes or water through tubes, like actual you know, relationships to predict motion and stuff, right? So he's applying this to the chaotic displacement in the band waves of the detector, and when they settle and become coherent. And through that, he also measured, what do you know, the same periodicity that Miller measured. So at his location, so real quick, Michelson-Morley 1887 was done in Cleveland at an altitude of 200 feet above sea level. Dayton Miller did his at Mount Wilson, which is 1,800 feet above sea level. And then Kharkov is about, I want to say 500 or 600. I can't remember off the top of my head, but it's not very high. But anyway, what he's measuring here are that same periodicity from Miller. So Galev did his measurements in 2001 to 2004, different series. And then he's measuring the same periodicity that Miller was measuring in the 1930s, right? Like the 1920s and 1910s. The same stuff.
Crazy.
Yep. The same stuff. And then we get into, let's see, the dependencies of the wave. So yeah, he's saying here, when you plot all that against sidereal time, etc., that's what it's, the implication is that the source is coming from the sky. So when we're talking about experimentation and reproducing results, we have Michelson-Morley producing a 5-kilometer velocity shift in a basement at 200 feet below sea level. We have Dayton Miller taking measurements at 1,800 feet above sea level in a more open flowing environment for the interferometer to receive the ether wind. And that corresponded to a velocity of 10 kilometers a second to 12 kilometers a second. And then we have Kharkov lad here measuring at about, what was it, like 6 to 8, I think it was. So like he was getting close.
The different elevations had different results, is what you're saying.
Yep.
Yeah, which totally lines up with what Bob was talking about a while back there with gyroscopes and about how he was getting different results on his gyroscope at different elevations.
Yep. Yep. And then, so let's see here. Got the sidereal fluctuations, dimensions corresponding. Okay, yeah, so we got, so we got first order effects, first order measurements, and the math analysis is first order as well. So all confirming the same thing, like the same analysis, the same observations that were made, like 30, 40, 60 years ago, and all confirming the same thing, that the source of the motion is not the rotation of the Earth. So here's he did another experiment, or another set of experiments too, over the course of a year. Instead of using the optical wave bands, he did millimeter radio waves, and he did that over this area here. Altitude. So let's see. So this is again the height effect and the altitude. So this is what it looks like from a side view. So he had basically repeaters at different elevations, and then what he was doing was sending horizontal propagation to those repeaters, and then he was basically measuring like what's the velocity gradient of the ether wind at this altitude at D versus E versus C, etc. Right? So we had, and these are first order as well too. So we had, the configuration was set up so that the radio waves were being sent from the top and from the bottom, so they're like crossing each other instead of like going from the top and then bouncing back or something like that. So he's doing a two-way there, and then this helped eliminate like statistical errors and noise and whatnot, because you're literally cross-referencing the same thing, and the expected result of like it traveling with and against the flow. So you already know how much it's going to be retarded by and all that, so you can make really precise measurements. And this is again in the nano. In the millimeter. What is this? Hang on one second. Yeah, millimeter wave band. So really precise, really fine measurements. So what we have here is in the radio measurements, when plotted, we got the same we got a periodicity happening again, right? And it's happening on going with and against. That's symmetrical. So we have a symmetrical periodicity that's measured with millimeter precision in radio waves. Very cool. So that's regarding east-west propagation, and that would put the speed at that altitude at 6.4 kilometers a second. So using that information and those altitudes, he derives a velocity gradient for the ether going to the, he didn't go any higher than Mount Wilson, but basically he established the gradient from 0 sea level to 1,800 feet, which is crazy. considering that there's no ether or whatever, right? All right, so we got here's the data plotted out. So some of this is from Miller, and then this is his data set, or his velocities. So he's just showing how he derived all that. And again, here's a view of what that radio link configuration looked like. So we got first order effects of velocity gradient being measured with increasing in altitude. So the independent variables would be the geographic latitude and altitude, and the orientation and time that the measurements are taken with respect to the time of day, time of year, etc. And then the dependent would be the fringes again. And again, first order mathematical analysis used for this. So whether
Do you
or
think
not
they have these set up everywhere?
Oh yeah, dude. I think this is like what LIGO is. They've got all kinds of
Yeah,
other
that's
stuff
what
for
I was
this.
saying. I bet they have so many of these all over the plane, just recording. Just, I'm sure you can almost predict what might happen when these things shift a little bit.
Yeah, they like do you like synchronizing GPS like literally depends on all of this. Like the clock flexion. Like it's so insane like how much all this matters, and they're just like, nah, it's Earth rotation. And it's like, dude, what? So yeah, even so we have kinematic measurements, right? So we got measurements of so what he's doing here with those wave bands and the hydrodynamic effects, right? We're applying hydrodynamics to the background medium, and we're getting measurements that correspond to different velocities and how long it takes for the turbulent and laminar flow to settle. So we're deriving like properties of the medium. But again, this is kinematics. It's measurement. There could be another causal mechanism for it, but the framework that we're working with and how it's corresponding to everything, it seems to be in line with an ether wind instead of nothing. All right, so we actually already covered Michelson-Gale Pearson, so we don't need to do that one. We'll get into Ruyong Wang real quick. So yeah, we're almost done, I swear. This
is awesome, man. I'm loving it.
This is the last few slides here. This is what I added. So we have relativity making the wrong prediction here. So for an inertial observer being in linear fixed motion, like constant speed, there should be no fringe pattern produced. So what Wang did in 2004 is using a interferometer with a linear configuration. And actually, this picture of the conveyor isn't. There's a better one that's not represented here, so I apologize for that. But what he does here is essentially, relativity predicts that an inertial observer would not measure a fringe, and we have this moving in uniform linear motion, and it's producing a fringe. We have a graph here that shows that there's a proportional relationship linearly to the velocity of the conveyor to the fringe pattern that's being measured. And then in one of the configurations, he has it set such that only the top part of it, he has it set up in like a parallelogram so that the bottom part is fixed, the sides move side to side, but they cancel each other out because it's just side motion. And then the top part is what's moving. And then he derives the so how earlier we were talking about the length of the apparatus and whatnot. Well, just instead of using the whole length of the apparatus, so if the motion being measured was relative to something else or whatever, you would use the full length, but he's just using the length of the linear portion. And then when you move that, he makes measurements of that linear motion with respect to absolute space because it produces the fringe. And this is a direct falsification of relativity theory. It's a direct falsification of the idea that you can't measure linear motion. It's a direct falsification of C being measured as C for an inertial observer, in that all reference frames are equally valid and all that. So because how are you going to measure a variance in the speed of light directly proportional to your velocity if all frames are equally valid and the speed of light is supposed to be the same for an inertial observer? Like it's devastating, right? It's crazy. So this is a first order experiment, first order measurement, and the first order math derivation to explain it. And the IVs and DVs obviously are going to be the motion, so the moving linearly, and then the configurations, etc. So that's for that experiment. then we're going to get into Dufour and Prunet in 1942. So we talked at great length about the Sagnac effect and how, over the course of like 40 years, nobody could explain it, but now they just kind of teach it as an effect of relativity, even though it's clearly not, because relativity is a second order effect based off of first order effects like the velocity and the Sagnac effect. So the Sagnac effect being first order because it's a directly proportional relationship to velocity. Sorry, I kind of went a little fast there. Is that making sense so far?
Yeah, I got you.
Okay. Cool. So these guys, Dufour and Prunet, were like, okay, well, let's see what we can do here with a different configuration on the setup, right? So what we're looking at, and it's a shame that cameras didn't exist or whatever back then, and all we have are these terrible photographs. So anyway, what they have on this setup here is that the bottom is stationary, the top portion rotates at a fixed speed, and then on the lab wall, there's a recorder in the source, right? So they ran this setup with several configurations, one of which was the recorder being on the rotating device, being on the stationary portion of the device, and also being fixed to the lab wall, and same with the recorders. And more importantly here, though, is that they all measured the same thing. So there's a 4-inch gap between the stationary portion and the rotating portion. And then obviously the recorder being fixed to the lab wall. Now, whoever's making the measurement, whatever that position is, determines if it's an inertial frame or not. So if you're recording and you're in motion, you're not in an inertial frame. If you're fixed to a lab wall, you're in an inertial frame. So what they measured here is a proportional variance in the speed of light with, to that rotating device on the lab wall, on the rotating device, and on the stationary device. Now, relativity says if you're fixed to a lab wall and you're not even in rotation and the light's just traveling at its fixed speed, because, your boy light travels at fixed speeds, it would not produce a fringe pattern. So to explain this, they had to bring in Paul Lavaux again, the relativity fixer, right? The guy who proposed using general relativity to explain it, and then still invoking the geometrically convenient position. And by geometrically convenient, all these people mean, all of them, 100% of them mean, is the absolutely mandatory position to explain this phenomenon. So what we have here is for the lab wall prediction, the classical theory makes the full prediction based off of the area of the device and having the recorder at the lab wall. And relativity theory makes the wrong prediction. It's off by a factor of 10. And they have to invoke. So Paul Lavaux says like, oh, well, whatever, man, we have to treat it as an acceleration and use general relativity. Like that was literally his answer. So there's no refutation to this. It directly contradicts everything. And I think that's why they don't use general relativity to explain the Sagnac effect in gyroscopes anymore. Because it's overly complicated and low-key R-worded. So they just go with the time divergence with respect to a geometrically convenient position at the center of the device, which is mandatory, but don't tell anyone, because the math that Paul Lavaux used to solve the Dufour and Pruner situation didn't work out. There's a lot of air quotes. I don't know if that applies to an air quote situation, but it was fun to do it. All right. So now we'll get into the double slit experiment. So we have a light source and we have a wall here that basically is going to block the waves, and then we have a setup where the waves can be recombined through 2 additional slits. Now, if light's a wave, what's going to happen here is that the peaks and troughs of the waves are going to cancel out and create dark spaces, and the peaks of the waves, when they intersect, they're going to create bright. They're going to create bright patches. Like they're going to create an interference pattern basically across the length of this. Now, if light is a particle, right, if there's a wave particle duality, when you introduce the double slit, you would only have two portions that were lit and 2 portions that were dark, right? It wouldn't create this fringe pattern of recombining waves that are intersecting and canceling each other out, right? So they'll get into the modern quantum theorist would have to say, well, there's a superposition in the wave. The particle is passing through both of those, and it's interfering with itself, and it's collapsed because you're measuring it or whatever. It's like, okay, dude,
because you're measuring it, not when you're not measuring it, only when you're measuring it.
Exactly. And then so we'll get into that a little bit here. So there was a woman on YouTube, PhD quantum lass, who during lockdown did some experimentation with the double slit, and she found that, oh, light's a wave the whole time. So we have the light source here, and we have smoke, and then there's the double slit thing is, in the middle there. But anyway, what she has with the smoke is it's showing all the this recombining pattern here. Like, see how the waves are diffracting and then overlapping when they're recombining, which is creating the peaks and troughs intersecting and the peaks intersecting to create that. So each one of these waves band is represented in the smoke. I'm sorry, yeah. So you can see each one of those beams, right? So if it's a particle, it wouldn't be that at all. You would just see two creating their pattern, but that's not what happens. So she was like, oh, wow, that's really interesting, because I thought that that the wave was the abstract of reality, and that when we turn on this laser, particles are coming out, and then when it's traveling the distance between the source and the detector, it's a wave, which is some sort of abstraction, and then when it gets measured at the wall, that's when it becomes a particle again. So she actually has it completely backwards, because I think we touched on this earlier. Schrodinger puts out his wave equation in 1924, solving everything as a wave, medium, oscillation rate, blah, 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 right? All the classical mechanics backed up by it. And then Max Born comes along, and he's like, yo, if we square the solution to this wave equation, we can say that the electron exists as a statistical chance of probability in here, and it's bouncing around. And then Heisenberg came along and was like, yo, the more precisely we can calculate the momentum, the less precisely we can actually know its physical location due to quantum entanglement and superposition, blah, 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 right? And so, it's taught like completely backwards, because the abstraction is literally squaring the already solved thing that gives you the answer already. Anything additional is just for funsies. So again here, so a lot of people will say that this is a demonstration, not an experiment. And the IV is your consciousness or something like that. The actual independent variable is the slit configuration, because what they do here is sometimes they'll cover one slit, sometimes they'll cover two, where they'll have them both open, and it's supposed to each one of those results can be explained by a particle theory or wave theory, but when they're both open, it can only be explained by the wave theory. So it's the independent variable is literally the configuration of the slits. And
it's not a person watching?
No, that's insane. And so the dependent variable would be the pattern that's measured on the wall. And this is a first order measurement. You're introducing, that's it. You're not making any assumptions at all. You're just looking at what's being measured on the wall. So first order in that. So again, we have light still behaving like a wave, in case anyone wasn't sure. Over the last 100 years, it's still waving out. And then just to give a topographical view of what this smoke pattern that she's measuring would look like. So that's what she measured there, obviously being in tandem with the wave. Now, interestingly enough, you can introduce another variable here to the double slit experiment. And this is kind of blurry here. You can't see it very well, but this is a heat gun. Now, Alan, why would you heat gun light waves go into a wall? That's that's R-worded. Well, they say in quantum mechanics that the reason quantum computers don't work / are hard is because of ambient temperature in the background collapses the superposition. And if you collapse your superposition, you don't have that nice duality state where you can do all these calculations at once and then just pull out one, aka have a random number generator and pretend you're doing quantum stuff. But anyway, the big thing that they say is that it's the ambient heat that collapses the wave function. So we're measuring, the wave function here, right? So can we collapse it into the particle function? If we introduce heat, will this diffraction pattern become two beams instead of an assortment of beams? No, not at all. Not a single effect. So we have another example of that. And this is from an excellent channel called if you go to YouTube and search, if you type @itsbs, his YouTube channel is an excellent resource for all things quantum and special relativity and light and all that. And he actually does, his own experiments and things to show this stuff. So yeah, here he is doing his own double slit and introducing heat and failing to collapse the wave superposition into the particle duality, right? Now we have
observer-based dependency thing. It's making me remember someone brought this up when it came to the simulation theory. We all live in a big simulation, and this was a big thing when it came to that.
Yeah, dude, that's how they hook people, man. Once you buy into that, it's like it literally retards you, and then you start coming up with things like, oh, the consciousness of the observer, and it's like there's literally slits that you're manipulating to change the outcome. It's not your mind. So, but the reason why it comes to your mind, though, right, is there was a follow-up experiment called the quantum eraser experiment. Now, when you get to the diagrams of that, they can get a little overwhelming, but this is the most basic diagram I could find. We have laser, we have a beam splitter. Now, what happens here is it splits it through a series of one slits where there's a detector and a series where there's a double slit followed by a single slit. Now, you can change the configurations of the slits. You can block the top one, in this configuration, you wouldn't block the top one because it's supposed to be a simplified configuration, but you would adjust in the double slit portion. You would cover one of the slits, left or right, and then you would, that's all you could do with this configuration. But anyway, it's the same as the other ones, but it's just simplified for the ease of looking at it. But anyway, based off of that configuration, what happens is half of the fringe pattern goes to one detector and half of it goes to the other. So what they say is, what must have happened is light retroactively changed its status and became a particle. Nah, it's not what happens at all. When you combine the fringe patterns on both detectors, it makes it as if it was the singular pattern from this thing. So it's not particle duality. It's not changing its path. It's not altering it based off of your consciousness. That's literally a ruse that they tell people to make them believe that it's just a quantum weird effect. Like they have all this abstractness because it's literally that simple. It's splitting the interference pattern against two detectors. So when you combine the detectors, you get this. But because you're looking at it through, because when you're looking at it,
more people need to know about that.
Yeah, it's crazy because they have to present it that way to make it like it's a mystical thing. Like, it went back in time, it quantum entangled. Well, we just debunked quantum entanglement and superposition right here by introducing heat to a wave function. Why didn't it collapse? Why? If it was like, you know what I'm saying? So like this, it's like literally that easy, like natural science, bro. Light source, heat. Well,
we can test
it's over.
It. Yeah.
Yep. And then, so when they say, well, based off of the slit configuration, that's altering, and then when you can't tell which one it went through, so you don't know until you measure it. Yeah, dude. Well, unfortunately, when you combine the patterns, it's just this again. It was always this. So that's a wrap for quantum erasing and double slitting. So now we're going to get to the actual, in my opinion, the actual best proof that they give for wave particle duality and the substantiation of Einstein's conception of the photon, right? So in Einstein's paper, one of them, I forget which one, but he introduces the concept of the photon where he gives the E equals HV derivation from, what's his name? Max Planck. And he says, if we apply this, the light will be made of quanta, blah, 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 right? So the experimental verification of this comes from Arthur Compton, who did Compton scattering. So what we have here is a device that generates X-rays, an X-ray tube, and then you can send them out through a collimator, so they're going in like a coherent beam, like in a straight line, and then that's going to hit a graphite plate, and then that's going to bounce off into another detector. And based off of that, they're saying, there's an angle of incidence, there's a recoil, and there's a scattering, right? So what we're looking at here is that the classical theory, they say that there's a scattering for the recoil right? So there's an electron that's stationary on this graphite plate. Your X-ray, your photons coming in, it hits that stationary electron, which has to be stationary so that it has no kinetic energy, so that this calculation can be fully reified and calculated by the relativist. But anyway, what they do with that is they get their expected proportional value, which fits in with the classical prediction as well, based off of the angle and the energy input of the wavelength of the X-ray. But they also measure this additional output at a scattering angle. And they say that energy output, this shouldn't happen unless there's a quantized particle of a photon, interacting with an electron exactly as their model demands an explanation. And they say that they can only explain this effect through relativistic math, 4-vector math, meaning they're using the time as a coordinate in an XYZ coordinate system. They can put things in there that have no dimensional values, essentially, because it's an abstraction. And they're like, where do we put this abstraction? We'll put it in time. So anyway, they do that, and they're like, okay, we can fully calculate this. This only is explained through our ability to use the time variable and put these dimensionless values in there and do our computations, and what we get out of it is only explained through relativity, blah blah blah, right? So this reifies the conception of the photon as a particle, and that it's directly proportional to E equals hv, and it reifies quantum mechanics, because that's all the duality is based off of that. If it's not E equals hv, or I'm sorry, E equals h newing, then it's not valid or whatever, right? So this is all highly dependent on this, and this is what they did here. So this is not now what they let's see here, let's back up a minute. So on this scattered angle here, the energy produced from this has to be a certain wavelength, right? So its frequency is going to be proportional to a certain wavelength, right? In accordance with how the waves work and what the prediction is. So they don't actually, the way this apparatus works though, and the way that they do their measurements, this apparatus doesn't measure the wavelengths. It's not like an interference pattern, like an interferometer or anything like that. It sends the energy to an ionization chamber where it ionizes with a gas, and they convert that into an electric signal. And from that pulse rate, they say, okay, if the frequency of this of energy was this amount, then it would correspond to a wavelength of this, right? Now, the thing with that is that in this apparatus, you have the ionization is building up, you have the decay rate of the radiation that's being put out, you have all these factors in it that are building up in the ionization chamber. So they have to zero all that out and make sure that when they do, because you program what waves you're putting in for all this stuff too, so it's already calibrated to give you the result based off of the angle that you're putting it in. But anyway, to get to that point, they have to calibrate all that, and they're basing it off of the concept that it can only be explained through relativity theory. But unfortunately for and the quantization of light, but unfortunately for them, so in 1926, the year after Max Planck put out his 1925 paper saying if we square the wave function, we can role play, Schrodinger was like, let me put out a 4-part lecture series on how we turn the electron into a field, and we could explain the interactions through a field instead of assuming a stationary stationary part with no kinetic energy having an elastic collision with a photon. Instead of breaking it down like that, they can still explain it through just basically turning it as conceptualizing it as a field. So still being in alignment with classical mechanics, and they completely, so if we're still making the same predictions off classical effects and relativistic effects, and it's purely based off of the math, this device can't tell us if classical mechanics is correct or if relativity is correct by itself, because it's not taking a direct measurement. It's doing it through a conversion. So this is a second order measurement second, so interpreted through the conversion and what they already expect to get. And then it's sold to the public as a mutually exclusive proof of relativity because nobody can explain it without, the electron being in a stationary state or the elastic, blah, 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 right? But that's not what's happening. It's never been measured on the first order. And then to really drive home E equals HV, we're going to look at what's called the quantum flaw. And this was pointed out in 1999 by Julianne Morenstein. What she points out here is that, again, we have no time variable. So if we recall back to Newtonian gravity and all that, there's no time variable for that instantaneous action at a distance. But no, we got to disavow that, but still use the equations. All right, bro, just trust me kind of stuff. So when we get into the E equals HV, we have no time variable here, meaning this one would predict the wrong frequency for intervals less than 1 second. Because there's no time variable, it's bound to 1 second inherently, because that's what the original black body radiation curve was solved for. The data set was 1 second. So Max Planck, coming up with that quantization of energy over 1 second, over a 1 second period, is directly related to that. So that's why everything still works with C, because earlier I showed the Maxwell stuff about how it's all based off of an oscillation rate of 1 second. So this is why these line up and occasionally, make the right predictions. But why it's physically meaningless is because the no time variable, if you were quantizing light as physicality and you were interpreting it through this equation to substantiate that physicality, the quantization of it would be directly proportional to the frequency. So if you had the existence of the frequency, rather. So if you had a oscillation rate of 3 hertz a second for the frequency, right, that for a photon, that would the length, that quantization, and that H in there would be 300 million meters long. And we know that these experiments aren't doing 300 million meter long links, and there's no 300 million meter long quantized energy particle thing. That's not real, right? It's just purely an abstraction, purely kinematics. It does occasionally make the correct prediction, but without a time variable, you can show that it's not physically meaningful, because otherwise you would have to believe that the quantization part is proportional to the existence of its frequency, which would make it exactly as long as it is for you to see it, right? So you know how they say, oh, we see stars from zillions of miles away. Well, it's propagating through a vacuum based off of E equals HV. Sometimes it's represented as E equals HF. It's just frequency. And I'm saying V, but I mean nu. It's the little V with the line. So it's in that's all frequency. It's all vibration. So anyway, with that said, you would have to believe that the quantization part is 300 million meters long. And that's obviously not the case. So that's a direct refutation to it as well. And they've never fixed this. They can't really go back on it. Say you have a laser beam that emits a frequency for a red laser beam, and it's like one frequency away from degrading into a green color spectrum. So if you flick the laser on and off real quick, it wouldn't have enough time to generate that the frequency to be red. You would see it as green, right? Because it's sub 1 second. But you always see the red laser. You'll always see it with whatever color frequency it's corresponding to. So it's happening, not like not at the rate that they would need it to be if that's correct. If this equation was going to make the correct prediction based off of the length of its existence. All right. So in conclusion, we have the ether wind model. It seems to be intact. We have first order experimentation, first order measurements to back it all up. First order analysis. Relativity theory is in shambles, untenable, proven to make the wrong predictions regarding motion and the velocity of light in reference frames, etc., etc. Heliocentrism, untenable, no measured velocity, and it's been shown through experimental verification that relativity is wrong in stating that relative motion can't be, or linear motion can't be measured. So heliocentrism, untenable. Stationary Earth, super tenable, as the laws of physics were derived on a stationary Earth. They apply to stationary lads and lasses, and that's about all you really need to know. So
awesome, dude.
That's the conclusion.
So well done, man.
You've really done your homework on this stuff. I'm very impressed.
That's what I was saying earlier. These guys really have dug deep into how all this stuff works and all the measurements and, you know, all the people that are involved and what they actually say about it. And yeah, it's just just so eye-opening.
Yeah,
hearing
this will be one of those
again.
GLOBEbuster episodes that I'm going to be taking out that fine-tooth comb and combing through it, and yeah, just using that because every part of this can be dissected, and like you can just talk like, you know, an hour long on just Arago's prism alone. You know.
Yeah. The implications there are insane.
And yeah, so I'll be treasuring this for a long time to come.
Nice, man. Happy to bring it forward and present it, because there's you know, as like I was saying earlier, you know, when you come to this understanding that there's a huge deception going on, you put up this wall and you're like, all right, man, I need to know exactly what you're experimenting. What's your IVDV? Is this a man-made device? Is it real? Is it in nature? Does it exist? What are we doing? And you know, you really in doing that, you can kind of like block out things that are, you know, useful, right? And you can really like kind of limit your understanding and where you're going with that if you just hard cap it at that without going back to the history and trying to understand why things are the way they are, because that's where like I learned all this from, right? Just going over the history of it. And
you've got your puzzle pieces, they're all laid out, they fit together perfectly, and yeah, this is great. You see the big picture, and that's what I can really see.
Yeah, because like I said, they knew how fast Earth had to be moving. They knew that they could measure it, and when they didn't get it, like they redefined all the physics to say, oh, if you're moving fast, there's an extra special equation you have to use. What? It's like, what? It's like
extra special. It's like orbital mechanics.
Why is it extra special?
A little bit, shall we?
Yeah, it's like, why is it an extra special one? Well, because if you're moving super fast, you won't get the measurement that you think of how fast you're moving, and you actually have to use this math equation to pretend that it's that fast. And it's like, oh, I see what you're doing there. You don't have a velocity, and now you're lying about it through second order effects, aren't you? Yes.
I keep going on and on about math. People try to use math alone as a foundation, but I keep saying that just because 2 × 2 = 4 doesn't mean a yardstick is 4 feet long. Just say it over. Yeah. People still have a hard time grasping exactly what that means. It just means that you've got to take an actual observation and then use math to describe what you're seeing. That's it. Math is a describing word. It's just like a painting. You can judge how accurate a painting is by comparing it with reality. Okay, because I see this lady, I can verify that this painting is accurate.
That's a really good analogy. It's a really good way to put it. Yeah, that's exactly it. Because when you get into the math, right, you start abstracting things, space and time. Well, what did Einstein do with space and time? Okay, he multiplied time by the speed of light, got infinity, multiplied distance by the speed of light, just x, right, the coordinates. Multiplied that by the speed of light, got infinity, made a giant graph out of it. What does that tell us about reality, dude? It doesn't tell us anything.
But my painting looks so pretty, therefore it must be true. It must be accurate because it looks good.
Exactly, bro. The formalism of the painting is what counts, not what the painting is saying about reality.
Yeah,
that's exactly it.
Yeah, you get it. I'm very happy to see that, and you've got like a whole bunch of videos I've noticed on your channel there about math and just kind of how people are doing this. They're taking these mathematical paintings and treating it like that's the thing. That's it says it in math, therefore it's true.
Yeah, when you start breaking it down and looking up what they're like, you know, the Greek letters and whatnot, and what the variables are, what they're using it, you're just like, you just have a graph and you're just doing a hyperbolic conversion to get it backwards compatible with velocity. That doesn't mean it's real. That's nothing. But it's touted with such genius, and you can't understand it. You don't understand the brilliance of this math. Like, nah, dude, it's a graph, bro. It's nothing.
Yeah.
You're not going to graph me out and then gaslight me into thinking it's brilliant. because you don't have a velocity, dude. Get your own velocity, bro. That's like the ether wind model. We have a velocity component for our model, right? It's the same one that they measure with all interferometry ever, and we don't have to lie about it. We don't have to come up with second order theories to explain it or abstractions. We could take it for what it is, and that's where I'm kind of at with it, right? It's like the least amount of assumptions. And what are we actually measuring, and does it correspond to reality? Is there a hydrodynamic effect in light? Seems to be. Does light change? Does light have a velocity? Does the velocity of light measure differently at different times of year and day? Yeah, it seems to. So what does that mean? Well, it means that that's being facilitated by a background medium that's carrying that interaction, that's carrying that translation of motion. And when I say translation of motion, there's literally, like what we went over with Gale, Miller, and Morley, there's a vertical velocity gradient that gets stronger, that gets higher that gets faster as you get higher in altitude. That's not heliocentric. That's not Einstein. That's ether, baby.
Yeah,
that's
get
our
your own
predictions.
velocity, bro.
Yeah, get your own velocity.
That's a shirt right there.
Yep.
I've
Get your own. You can't have mine.
in quite a few Jeranism debates there, and so I'll be checking those out too. And yeah, I always enjoy seeing what they come up with, and I'm sure you've got all kinds of great responses to that. Those are always fun.
Yeah, so a big one was the correction angles for single axis gyroscopes, and how you would have to, how it would be a mutually exclusive proof of the globe, meaning that you have to orientate the device such that it's parallel to Earth's rotational axis, right? But what they're doing essentially is they're taking the z-axis and tilting it towards the sky, and that's on either model. But on their model, they're on their rotating globe, so they're like, tilted at an angle a little bit, a little antipodalness, so to speak. So that's what they think they're correcting for. Now, you wouldn't be able to explain that without an ether model in a toroidal field. So luckily, your boy's flat Earth model has an ether field that follows toroidal geometry. So we absorb all of those correction angles one to one, and we don't have to say things like, "Oh, that's a, it's a man-made device. It doesn't work. That's a parlor trick." It's like just nonsense stuff. It's like, no, we can absorb the technology one to one for what it is without having to change anything about it or make great leaps of logic. You can just take it for what it is. So that's why
the technology is based off of this.
Dude, it's all based off of this, and it really came together in GPS because it's a cohesive timeline that functions off of precise measurements of that, and observers at different velocities would make different measurements, and they could show that it doesn't. And within the crafts themselves, they would have to make relative simultaneity corrections because their velocities they would measure them different relative to the other crafts, because trying to keep it in sync. And those don't exist, bro. If the core tenet of your belief doesn't exist in reality, you're done. You're done. So that's what's up with that.
Well, that was awesome, Alan. Yeah. If there's anything else you'd like to present in the future, or any of the gentlemen over there that hang out Ether Cosmology and the stuff you guys are doing, yeah, just drop me a line and we'll set something up. This was just amazing.
Yeah, absolutely, man. And thank you. And like I said earlier, it's an honor to be here. And you said, I think it was you who said, it would, if Bob were here, he would have a smile on his face. And that makes me really happy because I started my flat Earth career watching you guys, and it was like breaking down the science and the technology and taking it to this depth, where that's what made it more fun for me and exciting to watch and stuff. So it's good that I'm glad that what I'm bringing is of that caliber, and that it's received that way.
Absolutely. Yeah. You've done very well.
Definitely.
Very, very much so. I've been very quiet because I've been just completely intrigued and listening.
She's been sitting here like this the whole time up at the screen.
Nice.
My favorite kind of show.
Yeah. I like the way you present it because you've got just constant information. I feel like I'm getting sprayed by a fire hose the entire time trying to get a drink from the fire hose. But it's not fluffy. It's just solid information.
Yeah, these are those shows you go back and watch multiple times, and And you can do so much research just from this one show. You don't have to go and study this topic and this person and this person. He's laid a lot of it right out there for you.
Mm-hmm.
Yeah, well done.
Yeah. Thank you, sir. Yeah, I try to include like a full spectrum of the narrative and steelman it as best as possible, because it's like the important part, like, you know, obviously as flat earthers, we started noticing that the people that believe in the globe there's a huge knowledge disparity in things that they know about the globular model versus what we know about it. So it's like, yeah, a big part of what I do is like to go through like what the official stuff is before I get into the other stuff, so that everybody can accurately be on the same page of what the mainstream is saying is, you know, this explains XYZ phenomenon. So it's like, yeah, the presentations get lengthy and stuff, but if you have to know like where it came from, who done it, who's doing it, why they're doing it now, are they still doing, you know, you got to go through it all. So
yeah,
it's a lot of fun.
Part right here is a kind of foundational piece that I think every flat earther, like who's really into the debates, should just analyze and segment it out and just really integrate it into their notes, because it's worth remembering.
Yep. And see, so I'm gonna hop off here, man. I got a couple of things to do.
Yeah, we're gonna wrap it up, man. Thank you so much. Give all your shout outs and any place people can find you. I put all those links in the description, places you can find Alan. I'm sure he's gonna shout them out right here.
Yep. So we're actually about to go live in about, well, would be 5 minutes, but I needed like 10 minutes. We're going to postpone it. But anyway, we're going to do a live reading session tonight. We're going to continue off of the Shankar physics book, the introduction into physics. So we're going to read that. And then Friday, of course, will be Flat Earth Fridays. Make sure you guys tune into that. Or there'll be episode 99, and then episode 100 the following week. There'll be a special thing going on, so definitely make sure you're there for that. If you don't have a Twitter account, you're slipping. Like, it sucks, and Twitter's horrible, but you gotta it's the battle, it's the current battlegrounds, boys. Get in there. And we already got a foothold established, so hit up Sacred and Proud on Twitter. That's the home base, so get right with the level heads. And then Sunday, I don't know if we have anything going on, but we might do a Brenner comp reading. And then Monday we'll do a Twitter space. Not sure what we're going to go over on that, but that'll just be community stuff. We'll just talk to people, see what's up. And then Tuesday again will be another presentation by someone. Hopefully Shane will be presenting on sky miles. So we've all heard there's a Haversine formula and it means that the Earth's a globe. Well, have you met my friend Shane and his spreadsheets? So we'll get into that hopefully. And yeah, we'll just run it on repeat, dog. And then we'll be reading again on Thursday. And Schooling the Globers Wednesday, and then Friday again, Flat Earth Friday. So man, shout out to the boys. Shout out to the Ether Cause crew. Like I said, we have like a full established crew. Like, it's just like, you know, you see Toby, myself, and Shane as like the front heads of it, but there's literally a full staff, dude, that back us up and help us. So shout out to the boys, man. You guys are great.
The amount of hours you guys put in over there, there's no way 3 people could do it alone. There's no way.
It's nuts.
Yeah.
Shane
awesome
probably
stuff.
could. He's an animal. He's not. He's different, dude. He's
so different.
He is different. He might be able to do it single-handedly. But all right.
All right, brother. Thank you so much. That was Alan from Space Audits, everybody. If you're not subscribed, go down in the description, click on the link, hit that button. He deserves it. We need to get these guys some more subscribers, for real. And not that it's going to help with the algorithms. I'm sure they're blackballed just like everybody else is, but you know, it gives them that drive to do more. You know, it really does help when you see your channel growing to want to do more. And I think that's a lot of what they do. They play on our emotions and our, you know, how we feel about things. And hey, if I can just turn off all of the, so he doesn't get any subscriptions anymore, maybe he'll quit doing this.
Yeah,
you know?
That's what they want you to do. It's a series of, it's like, to use the hockey analogy, shout out to my boy Andrew, who taught me about sports. So in hockey, there was a position called a punisher or something like that. And what this dude's job is to go around, and whoever has the puck, it's to go and fight that dude and make sure that he doesn't pick up the puck, to make you afraid to touch the puck. Don't touch it. There's someone's going to come beat you up. And that's all the globe has. That's all it is. Don't pick up the puck. Don't talk about FE cores, laser measurements, refraction. Don't pick up the puck. Nah, man, pick it up and run with it, boys. Score a touchdown or whatever you did with the puck.
Yeah.
Go sports ball. All right, Alan. I'll let you get out of here. I know you got your show coming up. Thank you again so much, man. That was awesome.
Anytime, bro. Peace. I'm gonna hop off.
All right, brother.
Peace. Yes. Thank you.
All right. Well, that's going to do it for our show as well. Go check out Alan's channel. There are some amazing presentations just like that, the one he just gave. So go give him a sub, show him some love. These guys deserve it. They're doing a lot of work, keeping the fires going, the FE fires. It's so cool seeing all these younger people picking up the reins and just running with them, like you, Kyle. Like, I know you've been at it for a while, but it's just awesome.
They're going through some really intense material, though.
Yeah.
They're really
very
going through.
deep.
They're basically going through college level material, and they're breaking it down, and they're helping other people learn how to break it down and understand what they did with the math magics, as he was just explaining. So it's pretty intense, but it's necessary.
Yeah.
It's
Flat
really
Earth is the best thing for my education ever. I'm telling you, I've learned so much.
I don't know anybody who didn't learn more after they got into this, than most of the time before.
No, I learned more in the last 8 years or whatever than I did in all of high school and probably up to that point.
Absolutely, yeah.
It's crazy. Yeah, it's like being born again. That's the only way I can describe it. Is I look at the world with totally new eyes, and I want to learn the truth,
I think one of the major differences is high school is really diverse. You've got English and you got science, and you got all these other things, history. But with this, it's very focused. But at the same time, even with this, you're still getting kind of diverse in some areas too, because I'm learning about history. I'm still learning about science. And there's a lot into it, but it's still narrower than it was in high school, I guess you could say.
Well, all right, folks. We're going to say goodbye to the panel and see what's coming up. Miss Karen B., did you have a nice birthday?
I did have a very nice birthday.
Well,
Very
good.
nice.
I'm
Thank
so
you.
glad. Are we going to have a scripture study this weekend?
I'm not sure, to be honest with you,
Okay. All right.
because our friend's having a birthday party for their little one.
That's right.
May
Okay.
is really popular for birthdays, I'm telling you.
Yeah, it is. It is.
So I'm sure we will see you Monday morning about 9:30-ish for a coffee talk.
Yes.
Awesome sauce.
Yes.
And then Tuesday nights, really late for me at 10 p.m.
It's
I'm
late
an
for
old
me too.
granny.
Yeah, it's late for me too, man. I'm drinking coffee to be on Strange World.
But yeah, Strange World with Mark Sargent, awesome show.
Yeah.
Always re-listen the next day. I got to get my Strange World in. Yeah, all right. Well, Kyle, what do you have coming up this week, sir?
I'm doing more common ground debates. I've been branching out into electrostatics and really talking about that stuff and really implementing a lot of the old time content with Bob there and kind of sharing what he had to say with the really stubborn globe earthers and kind of watching as their kind of the lights are starting to turn on. And it's really fun to actually watch people change their minds. They start off with being totally polarized on one side of the things, and then with the common ground debate approach, you kind of watch them starting to move. And that's the total fun of it, is how often do you really see that in a debate? Like,
Yeah, somebody concede.
That's my philosophy, is no one truly wins a debate until someone changes their mind. And sometimes they'll get me to change my mind on things, and other times, I'll change their mind. But that's part of the fun of it. Just when that's the primary focus, that's what makes it fun for me.
I mean, somebody's growing there. you know.
Yeah, and
It
I'm
really
I'm
does.
happy when they can prove me wrong. I'm
Then,
happy.
yeah, you grow
I might be a
too.
little bit kind
Yeah,
of like grumpy about. I'm like, oh my goodness, but
you're
it's still
right.
fun. It's still fun. Yeah.
Awesome. And Cammy, been kind of quiet. I know that was just you were locked onto the screen most of the time listening. What'd you think about the presentation?
I thought the presentation was outstanding. And again, I thought that mostly if I said anything, it would interrupt the flow. And I really liked how coherent he was keeping it. So it was not a lack of interest. It was quite the opposite on why I wasn't
Yeah,
involved.
same here.
And I was learning and taking notes on some different things. Again, he goes deep, and I love that. I think, again, it's the key to see how they wove the lie, and you get to reality by it because you unweave the lie and you can start to, again, put it all together. And such important pieces for people that don't like this. I admire the work that goes into it. So again, it couldn't have been a better presentation. I'd love to have him on again and even more interact with him more sometime when it's not such an intense presentation. But I really wanted to I knew that he had a lot to get through tonight.
Yeah.
Just getting his opinions in here as we're just talking about other things out there would be fantastic.
I had so many comments I kind of even thought about making, but again, I didn't want to break the flow. So it'd be good for a conversation, but his presentations are so out of this world and so deep, and he does such a good job in putting everything together for him. It's so appreciated. Again, these people are so talented. What I have going on, I think we might have it tomorrow night, but I have mostly I'll be starting to research our next week's show. We're going to be doing a deep dive on the Urbano Monte map, also called the Bonamonte map. It's that giant map that's 10 feet planisphere map with so much intriguing detail on it. There's so many different ways and so many details into it that I think it's going to take me a week to collect notes for it, looking at freshly. So anybody else looking at it, but again, just looking at it fresh on. And for those that are not familiar with it, it is they call it an extraordinary, and I think it is a 60-sheet manuscript world map in a planisphere that when put together is 10 feet in diameter with all kinds of intriguing artwork and details and things that for a map from 1587 make you wonder, how is that on the map? How did it get there? And why, like again, if
it's a head scratcher. Some of the stuff you see, it's like, what? Yeah.
Some of it's a head scratcher, and some of it is again, well, how did they know this then? Supposedly,
yeah.
If it's what they're telling us about these cavemen and only having this and the whole, but what is this map from this year that has so much information on it? So
it sounds like a fun one. I can't wait. And for me, let's see. I know tomorrow night, I believe we're not having a Have No Sphere, but next Monday morning we'll be starting it off. Well, actually tomorrow morning, here in about less than 7 hours. We'll be doing Ironworks over at freeworld.fm or here on the YouTube's Iron Realm Media channel. We have a lot of fun. Not a whole lot of flat Earth talk. We do rip on NASA, Elon Musk a lot. He's one of our go-to. It's a lot of fun. But yeah, it's early, real early. We have a lot more people from Europe than we do the United States in chat. But it's a lot of fun. And then Sunday's GLOBEBUSTERS, of course. So I hope to see you all there. All right. Does anybody else have anything else? Are we good?
Well, I'll just throw out here before we go that I have been releasing the rest of the Flattoberfest talks. However, they are not YouTube friendly. So I've been putting them on Rockfin, Odyssey, and what's the other one? There's one other platform that doesn't censor. Rumble. Thank you, Cammy. Thank you. It's hard to remember. It's hard to keep up. So Rumble, Odyssey, and Rockfin has like the Amanda Vollmer one, Dave Murphy, and then I'm going
There's
to be
some good
releasing,
ones.
and then I'm going to be releasing Greg Reese, and then the Q&A. But there's stuff in there that I just can't put it on YouTube. I
Yeah,
just
they
can't.
won't. They'll get taken down immediately. Yeah.
But that's why we do things live, because we
Mhm.
want to say all the things and show all the things and not be censored. So that's it.
All right. Awesome sauce.
I'll
Well, that
also mention one quick thing in the chat. We have a clip from Russell Gregory that I think I saw it before that was hissing on the ether. We may, it's not going to be tonight. We're really late tonight, but we may again go into and look at that. I think I looked at it last week, but I am letting you know that, yeah, it's hard to, without doing it, just go on live and play these things that we don't have queued up. So just that, Russell. We'll look into it though.
All righty. Well, so that's going to do it for tonight's show, folks. I hope you enjoyed it. That was an amazing presentation by Alan over at Space Audits. Yeah. Remember, be good to each other. Don't lie to each other. Open your mind because there's truth inside. Peace out, everyone.
Peace.